So shall I start?
Just wait, sir. So may I start, ma'am?
Yes, please.
So very good morning to all the eminent speakers and participants present over here. Ladies and gentlemen, I, Yogesh Kumar, host for the day, would like to welcome you all on day 2 of the 10th annual convention of IAPT RC-1 on the themes experimental learning and integration in physics, competency-based question in physics, and use of online tools, teaching methods, low-cost experiment in offline teachings. I'm happy to inform you that this session is being recorded and streamed live on YouTube. Again, this is a reminder for all the participants and speakers that time allotted for invited talks is 25 minutes, followed by 5 minutes for question and answer. Attendance form will be shared at the end of the session. Filling of attendance form and attendance on both days of convention is mandatory. Then only you will be entitled for the certificate. Attendance link will be shared personally. So kindly fill it during the session only. So without further delay, I would like to invite our first speaker of the day, Professor C.K. Ghosh, former Director, NCIDE, IGNOU Delhi. He will talk about some thoughts on learning of physics in the light of recommendation on NEP 2020. So I welcome you, sir.
Thank you very much for this opportunity. My heartfelt gratitude and respect to all the esteemed participants of this program. It's a pleasure being with IAPT, RC, Delhi and Haryana. In fact, I have been a reasonably active member during my tenure in Delhi. And so in a way, I am holding a dual citizenship, Delhi as well as Kolkata. Now, let me share the screen. I'm going to talk on teaching of physics in the light of the recommendations of NEP 2020.
So can you make it on full screen mode?
I think it's full screen now.
Yeah, now, yes.
Right. So since the time is short, in fact, I was given to understand that I'll get 45 minutes, but then if it is 25 plus 5, so I'll have to curtail my deliberation. Anyway, what within the constraints of time, what I have thought that among the several recommendations of NEP 2020, I picked up these two, the stress on experiential learning, and this has been picked up from the recommendation document itself. In all stages, experiential learning will be adopted, including hands-on learning, arts integrated, and sports integrated education. Now, my special area of interest is, of course, sports integrated education. But prior to that, I'll also talk about my vision of experiential learning. Yesterday, we heard 3 excellent deliberations from 3 stalwarts, and all of them directly or indirectly emphasized on the role, on the importance of experiential learning. So my task is half done. Let me make this comment, and I hope all of you will agree with me that, well, we keep learning physics from nature, we keep learning physics from surroundings, but laboratory is the marked arena for exercising experiential learning. But then what is happening? What is happening in a science laboratory? Learners perform routine tasks. Well, a particular set of learners, when they are allotted a particular experiment, they come to the laboratory, try to find out their friends who had done that experiment earlier, and will try to ask how much you adjusted the current, how much you adjusted the voltage. So they do not exhibit open mind towards the experiment. And that is being followed. And along with that, my area of concern, of course, yesterday I got very highly inspired again about experiential learning and its application and its execution in different schools and colleges of our country. But again, let us also have an introspection about the scenario, and all of us are involved in this matter. Well, see, all the competitive examinations, IIT, JEE, NEET, etc., they only test the theoretical competence of the student, not the practical competence of the student, but physics is a practical subject. And the way in which practical examination is conducted, well, there is a lot of scope of improvement. And I don't want to elaborate on this point. All of you are very, very experienced teachers and evaluators, and you know what all is going on. My concern is gradually, on one hand, we get such inspiring talks by Professor Kishan Lal, Professor Vijay, and Professor Aluwalia, and we feel inspired to go for experiential learning. But on the other hand, I at least feel that somehow, after looking at the scenario, and which has got aggravated after the COVID, that physics is gradually getting relegated to a theoretical based subject. And one of the reason, I think one of the remedy is perhaps with us. Now, see the third vertical, what I have written here. They means the students use the laboratory notebook at home. Now, what is exactly meant by laboratory notebook? If we analyze it from the point of view of English grammar, the word laboratory is adjective to notebook, which means the notebook which is used in the laboratory, at least which is supposed to be used in the laboratory. But what the students are doing, and that has been explained, it's not my version. In fact, I've taken from a textbook written by a famous teacher of practical physics, G.L. Square, S-Q-U-I-R-E. He says that they take down the data in a so-called rough notebook. I have seen all sorts of books on a piece of paper, on a rough paper, in a diary, in some other notebook and whatnot. And then from there, they go back home and copy it down on the laboratory notebook. Now, GL Square says copying is a wastage of time. And then there is every possibility of committing mistakes while copying. And the most importantly, he mentions that there is an irresistible temptation of being selective. I am doing the experiment on Ohm's law. I have taken 10 observations, and out of them, 4 does not fall on the straight line passing through the origin. So while presenting my laboratory notebook, which is the so-called fair notebook, I just remove those 4 points and keep those 6 points. So what exactly I am doing? It is totally against scientific honesty and scientific integrity. I have taken an observation with my own God-gifted eyes, and I am removing them without making any analysis. So means I stretch it to the extent saying that if I am called to the court to give a witness, then standing in the witness box, I'll give a false witness. So we have to try and make the students write the data there itself in the laboratory. And I have tried that, but I have failed. I have failed miserably. I have tried time and again. In fact, you know, at one stage, way back in late 80s, I was an examiner of Calcutta University Practical Physics. And then in the examiners meeting, it was decided that the students will be asked to produce the notebook where they had actually taken the data. And when this was announced to the different colleges, well, bizarre things started happening. They started preparing rough notebook from the fair notebook. And all sorts of things started happening. Date of experiment is sometime in December, January, and room temperature is 42 degrees centigrade. Things like that started happening. So can't we try? I have tried with teachers at different colleges, in fact, colleges of education, and the teachers say, well, sir, at the time of examination, the external examiner will not agree. They would like to see a notebook which is neat and tidy. I don't ask to make them untidy, but if there is a data which for some reason or other cannot be accepted, we just make a line through and say, and give a remark that why you have not accepted the data which you have observed yourself. So through this platform, it is my fervent appeal to all the teachers that let us try to make it happen. Well, at least as I was saying that I failed miserably, but during this practical physics examination of Indira Gandhi National Open University, since I was holding a responsible administrative position, it was not possible for me to be there for the entire duration of practical. But in one case, I did, sacrificing every other activity to see this happen, and it could happen, but it happened only for those 10 days or so, and later on it again fizzled out. But if this happens, at least we can ensure scientific honesty and scientific integrity among the students. I once again make an appeal to all the teachers, because this is a platform where I think I can spell out my concern and request you to see that this thing happen, that they take data on the laboratory notebook in the laboratory itself. Only one notebook, no fair notebook and rough notebook. Now, since I'm talking about experiential learning, I would like to share some experiences. In fact, I was taking higher secondary practical, and in the practical class, well, normally there will be two teachers, and the other teacher was a very senior colleague of mine. Now, a student comes and says that he has obtained the specific gravity of copper sulfate solution as 32.7. So my senior colleague, he just took the exercise book and just threw it in front of him, that you have made a great discovery. Repeat. So, but that student was very much after us. He was asking that, sir, please tell us what mistake I have committed. And so much so that at one stage I told my senior colleague, since he was senior, I first didn't object to what he was doing, but then I requested him, sir, since he is pleading, let us see. But then I asked him that, do you know mercury? What is the specific gravity of mercury? He said he knows, 13.6. So that means you feel that in that beaker, instead of copper sulfate solution, had there been mercury, then what would have been its weight? It would have been very heavy. But then I said that, but according to you, this solution would be 2.5 times, almost 13.6 into 2.5 will come to 32.7. It's almost 2.5 times heavier than mercury. Have you considered that? So he started scratching his head and said, yes, I can understand, but please tell me what mistake I have committed. Now, then I found that he has used this working formula. SC means specific gravity corrected, SO means specific gravity observed, into rho T, that is, rho is the density of water at T degrees centigrade. And then he showed me the textbook which he has used, and there the formula is written like this. There is a printing mistake, that T has come after rho, not as a suffix. So what has happened, the specific gravity of copper sulfate solution is 1.09, and density of water is roughly 1 in grams per cc, and temperature of the day was 30 degrees centigrade. So he multiplied that and it comes to 32.7. Now, he was not a good student, because see, here rho is grams per cc, this is degree centigrade, so a kind of a weird unit of specific gravity will come. So he should have applied his mind to that specific gravity is a dimensionless quantity and it cannot happen like that. So he was definitely not a good student, but I can't help appreciating his honesty. If such a student, because it was because instead of rho T, it was printed as rho T like this, and that caused the damage. So if such a student, that's my feeling, is nurtured properly, then because he has the scientific integrity, he has the scientific honesty, and so if such a student can be nurtured, then definitely we can develop interest among the students in practical physics. Another experience I remember, again with our IGNU nursing students, not of science students, they are BSc nursing students, and they have to do all sorts of practicals. And in one of the practical, most of the practicals are based on medical, surgical, nursing, and different other areas of nursing, but they have to do practicals in applied sciences. And one of the practical was verification of the parallelogram law of forces. Now, IGNOU does not have its own infrastructure. We have to go to different colleges to hire infrastructure. We go with a golden bowl that we say that we will pay this much of higher charges and all that. But in the laboratory where we had gone on the day of the examination, it was found that they do not have any setup for this parallelogram law of forces. But I, with one of my friends at that college, could take some of the corks available in the laboratory and then the wet boxes, and then we could somehow manage to make this setup. And I was about 30 years younger at that time, and so I was feeling quite elated that they said that this experiment will not be possible, but in no time I have been able to set up the apparatus. And that was a kind of a pseudo pride in which I was basking at that particular time. And why I'm saying pseudo pride, because when I was doing this setup and explaining the arrangement to the students, I heard some of them whispering at the back that, see, this is the arrangement we use for giving traction to an orthopedic patient. This is the arrangement we use for giving traction to an orthopedic patient. It is giving me goosebumps. Believe me, I have never felt so ashamed in my life that I know the experimental setup of parallelogram law of forces. I know its theory, but I do not know the application, which these girls know who have not studied physics in their school science courses. So this was a big lesson, and this was spelled out by all the three speakers yesterday, that the impact of science and technology on society can be felt when it benefits the common man. This is R.K. Lakshman's common man. So this is something which we should remember. So much about experiential learning. And then let me talk about this application orientedness, which I've already mentioned, and the spirit of inquiry should be there. I'm not elaborating on this point, but let me quickly go through some historic moments from different sports. Sir, how much time, Yogeshji, I have?
Sir, you can continue. You have more than enough time right now.
Okay, so let us see some historic moments from different sports. Now, the first one is the ball of the century, which is also called Gatting ball. Mike Gatting, bowled by Shane Warne, in the first delivery he made in England. When he came to England, this was a menace. This has to, this advertisement has to end, and then only we can get to the this advertisement has to end, and then only we can go to the main presentation. Yes. So here you can see Shane Warne, and he is about to bowl the first, and see the bowling analysis of Shane Warne. 0 over, 0 maiden, 0. So this is the first delivery he is going to make after in English soil, and he is bowling to Shane Warne, and see what happens. Shane Warne is a leg spinner, as you know, famous leg spinner. Unfortunately, he passed away this year. So Shane Warne to Mike Gatting, and this is called the ball of the century, sometime in 1993, June 1993.
Sorry, sir, we are not able to see the video of what you are.
Yes, sir.
You're not able to see the video?
Yes, sir.
What should I do?
On the link, you press Control as well as a mouse key.
Control and?
Control plus mouse key. You enter the mouse key. Press Control and enter the link.
So then I'll go back to that.
Yes.
I'll control and then enter the link.
Yes.
Sir, have you opened the link also? Have you shared the link?
So this is on YouTube only, na? From
Right,
which
right.
Yogesh, can you play it? I mean, it's possible.
Yeah, it's not coming now.
Control has to be pressed along with this.
Control S.
Control plus link together.
Control plus click together. That's what I have done.
Sir, that window is not shared by you. You have only shared PowerPoint window.
You have only shared the
PowerPoint, yes.
PPT. Yes, sir. You will have to share the entire screen. Then only it would be visible.
Yeah.
And audio also would need to be shared.
Yes, yes.
You can stop share screening and then share it again.
So, sorry, madam, kindly repeat.
Stop the screen sharing, sir, and
So
then
first
share
stop,
it again with the this thing open.
I'll stop the screen sharing.
sir, I have stopped the your screen now. Now you can share your whole screen.
So now I'll go to share screen.
Yes.
Then
Browser
Share the whole screen. Instead of window, share the whole screen.
Also tick audio box, sir.
so I've come back to the PowerPoint. Is it coming now?
not yet, sir.
No.
If it is playing on your screen, sir, you please minimize the PowerPoint presentation. Minimize that.
Sir, don't share PowerPoint PPT. Share the browser window where you have opened the YouTube video.
Can we share this video, Yogesh? कि हम इसको गूगल पे करके हम इसको प्ले कर दे और सर
Yes,
इसको
sir.
वर्क
Yes, sir. If you send me the link in the chat
Sir,
box, then
I link I do not remember. You just write getting ball on the.
you just share the title screen once again, the slide in which there was a title of this YouTube link. We'll just type it and then any one of us will share it. This Shane Won slide you have, no?
sir, can you tell the title?
Getting ball.
Getting ball.
BATTING, the ball. Shane Won betting the ball. Yes.
No, getting the ball. No, getting ball.
Spell out, sir.
Can you see the screen?
Yeah, Mahesh Shetty sir has
No.
shared the video. Sir, can you?
Yeah, I'm just opening.
Getting ball. And next would be
Can you see my?
Yes, we can see. Now you can explain, sir. Course, sir, can you see the screen?
I'm seeing my PowerPoint on the screen.
Sir, no, you see like the Zoom link in which you have attended the meeting.
Visible now.
It's visible
It's
now.
visible now.
Sir, can you see the video now?
Yes, it is visible. Video is visible.
I'm
Sir,
unable
can you
to
explain now? Is it visible to you?
Yes, sir, it's visible to all now.
It's visible to all.
Yeah.
Yes, sir.
Now, can you see it now?
Yes, sir. Yes, sir. We all can see.
Yes.
Okay. Sorry for my lack of technical knowledge.
It's fine, sir. You continue.
Now see the delivery of Shane Won.
Sir, we can all see the video. Is it visible to you or not? I think sir connection is freezes.
Is the connection lost?
Ma'am, I think so. That's why he is unable to watch the video. So let's wait for.
Okay. I'll just call him. Huh?
Yeah.
Yogesh, there is a power cut at sir's end. So Mahesh Sethi sir ko you can call. Meanwhile, he'll join after.
Okay. Okay. Now I invite Professor Mahesh Sethi sir. He is from Wilson College, Mumbai, Maharashtra. And his title is he will talk about building competency in scaling and order of magnitude estimation. So I welcome you, sir.
Thank you. Let me just share the screen. Thank you, IAPT RC-1 for giving me this opportunity to interact with our teacher colleagues. Am I audible? I hope.
Yes, sir. Yes, sir. You're perfectly audible. Please.
Yeah. So I will also would like to acknowledge IAPT Mumbai, where we have been conducting various kinds of workshops, and what I'm going to talk and share with you is outcome of that. Also, my friend Dr. Atul Modi, with whom I have interacted many times. So this is out of that. So let us talk about, we are talking about building competencies in scaling and order of magnitude estimation. And in the earlier talks, the sir was talking about the student getting confidence into, and as well as along with students, even teachers, getting confidence into handling the real life situation. And this is one particular skill where it is going to really help teachers in the first place and students eventually to get kind of confidence to handle the real life problems. So I'm just starting with a small quote from surely you're joking, Mr. Feynman. So here he mentions about his experience, how he started learning from his father in his childhood. So he has written, we had an Encyclopedia Britannica at home when I was small boy. He used to sit me on his lap and read to me from the Britannica. We would be reading and say about dinosaurs, and it would be talking about something like, say, T-Rex, and it would say something like that encyclopedia entry, that this dinosaur is 25 feet high and its head is 6 feet across. Now my father would stop reading and say, now let's see what that means. That would mean that if he stood on our front yard, he would be tall enough to put his head through our window up here. So, and he mentioned further that we were in the second floor, but his head would be too wide to fit in the window. Now, he is talking about the numbers the numbers which are mentioned here, 25 feet high and 6 feet across. What Feynman further comments is everything he read, that is his father read to me, he would translate as best as he could into some reality. And this is where one of the very important skill comes, that whatever numbers we are looking at, okay, how to make meaning out of those numbers. And we need specialized practice for working on those kind of things along with it, and the confidence comes slowly as you start working on it. So let's talk about some examples. Here I'll be sharing some of the examples and how we can slowly go on building up this kind of skill. What kind of problems can be given to students, what kind of problems we can design, and what kind of problems, even as a pastime activity you can work on, because ultimately the skill comes when you work on it for a long time. And why am I saying pastime activity is because many of these problems are either order of magnitude calculations, and nowadays with calculators available in mobile phones, and mobile phones are always available with us, any new idea clicks, okay, you can quickly do a small calculation. And though there are scientific calculator apps available in the mobile, even with simple calculators, some of these things can be done quickly. So let's talk about, recently I was talking to a group of students from class 11, and I just asked this question that, okay, what estimate the number of atoms in human body? I was talking about the 3D printing technology and how teleportation, different steps in teleportation can become possible in one of the popular level lectures. And then I said, okay, let us estimate number of atoms in human body. The first question I asked is, okay, what is the approximate mass of human body? So that, of course, people can answer, and you may approximate this as 100 kilogram or 50 kilogram. Of course, 100 kilogram is too large. But then idea here is, if I want to estimate the number of atoms, okay, my answer may change at the most by 2 times. Okay, so based on our assumption, the final answer will change by half. If I take 100 kilogram, it will be double, or if I take 50 kilogram, then I'll get some number. So this number is not really going to be very important, because surely we are not going to go something down to 10 kilogram or something up to something like 500 kilograms. So this order of magnitude is perfectly fine. Next question, what we need to bother about is which atoms are there in human body. Now there are large number of different kind of atoms, but which is the most abundant? And one answer which many students gave is, because that is what we talk about and we emphasize in biology, that it is all carbon-based life. It's a carbon, but without realizing that 70% of our body is water, and there is 2 atoms of hydrogen in every molecule. So lighter atoms will be the most abundant, and that will dominate in our count. So we have to keep that in mind when you are talking about, say, number of atoms in human body. And 70% is water, and then you can talk about the average density is close to water for human body. Okay, so hydrogen becomes most abundant atom. And then what is the mass of hydrogen atom? Okay, now of course, a good physics student should know what is the mass of hydrogen atom. That is one thing. Okay, but many times what happens is, this is what I have observed at multiple places. Students don't remember mass of hydrogen atom. But if you ask them what is Avogadro number, I have seen everywhere people have remembered Avogadro's number. 6.02 10 to 23 is what they will say. without realizing that reciprocal of that is mass of hydrogen atom. So if you use an SI system of units, then it is kilomole, and then it is 6.02 into 10 raised to 26, and reciprocal of that 1.67 into 10 raised to minus 27 kilograms. So that's mass of hydrogen atom. And then it becomes easy to calculate that you are talking about something like, say 100 kilograms, if I say 10 raised to 2, and then I'm dividing that by mass of one hydrogen atom, which is of the order of 10 raised to minus 27, and then I get approximate number as 10 raised to 29 atoms are there in human body. Now this was a simple example, but starting with these kind of things, surely we can make them do simple, small order of magnitude kind of calculations to get an idea about the numbers that one handles. Now, let's talk about, say, estimate the total mass of atmosphere. Okay, how does one do that? So everybody knows mass of Earth. Okay, I mean, generally those are written and many people remember that. But suppose I want to estimate the total mass of atmosphere. What will I do? So which principle will I use? Now, one of the principle which can be used is, we know atmospheric pressure, and we can estimate the surface area of the Earth, because radius of the Earth 6,400 kilometers is what many times people remember. And then you can do the calculation that what is 4 pi r square, and you can get that number. So that will give you the gravitational force by atmosphere on the Earth. So you have atmospheric pressure, which is about 1 bar, approximately 10 raised to 5 pascals. And then the surface area 4 pi r square, and r So that surface area multiplied by pressure gives you the force, and this force is nothing but gravitational force of atmosphere. It is the weight of the atmosphere. And one additional assumption you will have to do, since atmospheric height is very small as compared to the radius of the Earth. Atmospheric height is how much? It is about we say about 10 kilometers. Surely it doesn't go beyond 100 kilometers. And as you go up, of course, it starts becoming less dense. So mainly dense atmosphere, if you consider, it is about, say, 10 kilometers or so. And then you can assume that when you go distance at 10 kilometers, okay, as compared to 6,400 kilometers, which is radius of the Earth, the G is not going to change much. The gravitational acceleration is not going to change much. And then you can say that, okay, I will use value of G as, say, 9.8 or 9.8 meter per square second, or say, even I can approximate, because I'm estimating 10 Newton per kilogram or 10 meter per square second. Now, this will give estimation of mass of the atmosphere. So what you've done is you've calculated the atmospheric pressure, which is 10 raised to 5. Then you are multiplying with 4 pi, which is approximately 10, and into r square, so 6.4 into 10 raised to 6 meters square of that. And then you can see that that value 6.4 square can be approximately 40, okay, and into 10 raised to 6 square, so that will be 10 raised to 12. And then you have 4 pi, which you have approximated as say 10. And so effectively you get something like 10 raised to 12 into 10 into 40. So that is about 4 into 10 raised to 14. And then you multiply with 10 raised to 5. So that gives you something like 10 raised to 19 newtons, and you divide by 10. So that you get approximately 10 raised to 18 kilogram as mass of the atmosphere. So 10 raised to 18 kilogram, you see, is very small fraction of 10 raised to 24 kilogram. So, but this is how one can estimate the mass of atmosphere. You can also go for more such kind of problems of estimating the amount of radiation by human body. Okay, where students have learned about Stephen's law. So Stephen's law is applicable for black body radiation. Okay, now can you assume that human body is a black body? Now, apparently not a perfectly black body, because whatever light is reflected on us, part of that gets reflected back. Okay, so we know that human body is not a perfectly black body. So, but there will be some particular coefficient, okay, that we will have to talk about. Now, that coefficient will give limitation on the net power given. Okay, but at the same time, we have to see that the amount of reflection that our body is going to do, or amount of absorption the body is going to do of whatever radiation falling, okay, that same coefficient probably will also play a role in giving out the radiation. So if I assume that it is a perfectly black body with small correction, then the power given according to Stephen's law is sigma T raised to 4 into the area. Okay, because it is the amount of power given out, amount of energy given out per unit time per unit surface area. Okay, so that we talk about is, okay, there was a question, but I'll answer that question immediately after this. That we are talking about sigma T raised to 4 into area. And sigma is easy number to remember, 5678, 5.67, 10 raised to minus 8 SI units. Our body will be emitting with temperature T1, which is at higher temperature, 37 degrees Celsius, easy number to remember, 310 Kelvin, because we have to write everything in absolute temperatures in this particular law. Also absorbing from surrounding temperature. So surrounding temperature we can approximate to 27 degrees Celsius. Okay, of course that changes, but say if I assume 27 degrees Celsius, then I know it is 300 Kelvin, easy for calculation. And then the power can be calculated using this. Now, one estimation here required is how much is the area of the human body. And that is an interesting question, can be asked to students. The student come out with very interesting ways of calculating. When I tried at multiple times with students, some of them assume human body as a cylinder, some of them assume one cylinder and a sphere on top of that, something like that, or part of a cylinder and then two cylinders for leg and then sphere at the top. Doing all this, okay, considering the say for example, if you're talking about the circumference is something like say 36 inches, then you can convert that into centimeters. It could be 90 centimeter, and then 2 pi r is 90, and accordingly you can calculate r, and then basically 2 pi r is what is important, because for the cylinder it is 2 pi r into height. Okay, and when you do that, the area, surface area, turns out to be about 1.5 square meter to 2 square meter, approximately around that. And then after doing this calculation, effectively the power turns out to be something like 100 watts. What does it mean? 100 joules energy we are emitting per second. Now, is it a meaningful number? So it turns out to be, yes, it is meaningful number. In multiple ways we can check that. Let me quickly write things on this. So we are doing this calculation. Just a minute. Let me just add a slide here so that I can write on that. Okay, so I wanted to do this sigma 310 raised to 4 minus 300 raised to 4 into area, and I said calculating all this number, this is approximately say 100 watt, which is 100 joules per second we are emitting. Now in one day there are approximately it is exactly 86,400 seconds. This is actually exactly, not approximately, but this is approximately 10 raised to 5 seconds, which means total amount of energy you give is 10 raised to 7 joules per day. Total amount of energy given out, 10 raised to 7 joules. And if you could calculate this into calorie, then we know that 1 calorie is 4 joules. And this would, and 1 kilocalorie will be about 4 into 10 raised to 3 joules. And when you divide this by say take 4 into 10 raised to 3 joules, this is the conversion factor effectively for kilocalories, you get number like 2,500 kilocalories. That is what we typically say is the amount of energy required, 2,500 kilocalories, the amount of energy required through the diet. Okay, so effectively what you are going to eat, all that energy, we are going to do less amount of effectively the mechanical energy is less, but total amount of energy that we are giving out is effectively the same order of magnitude. Okay. Okay, let me just see. I think there was some. Yeah. So basically, this is what we say. And then if somebody is doing extra mechanical work, then there are multiple factors taking into it, and then amount of energy, the energy consumption required will be higher. So there are different ways of looking at it. Also, we can say that because every person is effectively a 100-watt bulb, amount of energy given out. Say if 50 people are sitting in a room, okay, you really need good amount of ventilation or at least fan working, because otherwise it is something like 50 into 100, that is 5 kilowatt heater going on, and that immediately students are able to connect that yes, why you need the good ventilation when large number of people are sitting in a small room. Coming next to other kind of things, but let me just go to the question, some comments over here. Explain the conversion of power of temperature from power 4 to power 2. Okay, let me see whether this was a typing error. This was a typing error. I'm sorry for that. Let me just change that. This is typo error. Thanks for pointing out. So is my screen visible?
Yes, sir.
Yes, sir. Yes.
Yeah, thank you. Okay, now coming to another kind of question, like when people talking about the current flowing through the metal and the amount of we know if you take small small amount of material, we know we are talking about moles, which is of 10⁻23 atoms. But how many electrons are actually contributing to the current? So suppose I am interested in a simple case, the laboratory kind of case. A 10 milliampere current is flowing through the wire of thickness 1 millimeter. Okay, 1 millimeter thickness I have taken for easy calculation, but it is also close to 22 gauge wire, which is 0.7 millimeter, and 18 gauge wire, which many times 22, 18 gauge wires we use in the laboratory. If you're talking, I'm talking about single stranded wire. Okay, and then 18 gauge wire has 1.2 millimeter thickness. So I'm taking somewhere order of magnitude. How many electrons are moving per unit time per square angstrom? I'm saying square angstrom. Why? Because typical size of atom is an angstrom. So when you consider one particular atom, how many electrons are effectively flowing? That we want to calculate. Sometimes these numbers can be calculated just out of fun. I mean, you may not really make big application, but this gives you some good idea of the order of magnitude that is happening at this level. So 10 milliampere current is same as 10 millicoulomb charge flowing per second, and 10 millicoulomb charge is 10 into 10⁻³ coulomb divided by charge on 1 electron. So basically it is 6.25 into 10⁻16 electrons flowing. Okay, but that is those are the total number of electrons flowing through the entire thick wire. Now through 1 millimeter thickness, we have typically pi r square. If you consider 1 millimeter thickness is actually diameter. So if I take pi r square, then this is the 0.78 square millimeter. And when I convert that into angstrom, 1 millimeter is 10⁻⁷ angstroms. I get a number like 7.8 into 10⁻13 square angstrom. So that 1 millimeter thickness wire, if I consider the area of cross section in terms of square angstrom is this, and then 6.25 into 10⁻16 electrons moving per second per this much area. So per square angstrom, it is going to be about 800 electrons. Okay, so you see that about, you consider one particular atom, okay, about 800 electrons per second are flowing across that. Okay, this is one. I mean, this gives some interesting idea to students, at least at order of magnitude level, that how many electrons are flowing. To give some basic idea, this of course later can be taken for statistical analysis and those kind of things. But this inquiry into the numbers becomes very useful skill, and that can be developed right from the secondary school level. Another area which can be interesting to students is scaling. So if the sun is of the size of, say, 1 rupee coin, at what distance Earth will be placed? Now this becomes a good scaling model, especially the astronomy becomes a really good scaling model, or the atomic level physics also becomes a good scaling model. So sun is of the size of, say, 1 rupee coin. Now we need some amount of information that at what distance the Jupiter will be placed and at what distance the nearest star will be placed. We want to do these kind of calculations. So here what we can do is let's work out some simple calculation. Work out some calculation over here. 1 rupee coin. If you look at it, the radius is about 1 centimeter. So radius for is approximately 1 centimeter. And what is the radius of the sun? So either, of course, you can directly take information that it is about 7 lakh kilometer radius, or you can make an estimation that the 1 AU distance, that is Earth Sun distance, is about 1.5 into 10 raised to 11 meters, and the size of the sun is half degree. The diameter of the sun is half degree. 1 degree is approximately 1 by 60 radians. Actually, it is 1 by 57, but order of magnitude 1 by 60. So this is going to be about 1 by 120 radians, approximately 1 by 120 radians. This is diameter, okay, and the radius is going to be 1 by 240 radians. Now, the advantage of radians is, how does one define radian? Radian is the arc length upon radius. So straight away you can find out how much is this going to be. That is what we say, that the arc length is given by r into theta, and now this is 1.5 into 10 raised to 11 multiplied by 1 by 240, because theta is 1 by 240 for radius. Okay, and this you can then calculate approximately, I mean, as say 7 into 10 raised to 8 meters. So what you are doing is 1 centimeter, you are now scaling up to 7 into 10 raised to 8 meter, you are scaling down to 1 centimeter. Okay, and then at what distance Earth will be placed? So that is the question. Now we know here directly from this that Earth is effectively placed at 120 times the diameter, and therefore Earth will be placed 120 times the diameter of the sun. The diameter of the sun will be 2 centimeter, because the radius of 1 rupee coin is 1 centimeter. So 2 multiplied by 120, that is at about 2.4 meter, Earth will be placed. So you have, I mean, you can imagine then now a coin is here, and at around 2 meter distance, 2.5 meter distance, the Earth is going to be placed. What will be the size of the Earth? That will be 100 times smaller than size of the sun, approximately 100 times smaller. Similarly, you can find out at what distance Jupiter will be placed. Jupiter is 5 AU distance. That is what is written in the book. So 5 times 2.4, you can calculate, and accordingly at that distance, okay, about 12 meter distance. So at 12 meter, students can imagine how long is 12 meters. Okay, 2.5 meters, students can imagine how long is that, and they can imagine, they can see directly what is the size of 1 rupee coin. So this gives them some interesting ideas to imagine, okay, and look at how far the objects are placed within the solar system itself. And then you can, of course, calculate at what distance the nearest star will be placed. So here you are scaling down. Even if I consider this 7 into 10 raised to 8 as approximately 10 raised to 9, okay, I'm going something like a billion times smaller model I'm making. And if the nearest star is something like 4 light years away, so 4 light years, when you convert into meters, it is 4 into approximately 10 raised to 16 meters, and my scaling factor is of the order of 10 raised to 9 now. So when I divide by 10 raised to 9, okay, I'm going to get number which is something like 10 raised to 7. Okay, so 10 raised to 7 is, and in terms of what I have to do in terms of 1 rupee coin, I have to talk about. So 1 rupee coin was considered to be 1 centimeter. So 10 raised to 7 centimeters, that is 10 raised to 5 meters. That is about, no, sorry, 10, I 10 raised to 7, I have to, so 10 raised to 7 meters I will have to keep. Okay, and you can imagine 10 raised to 7 meters is how much distance? That is about 10,000 kilometers, 10,000 kilometers. So idea involved here is that sun is at one place. Okay, the others, the nearest star is going to be at very long distance, and that distance is a few thousand kilometers. And few thousand kilometers, when you're talking about, it means there is a lot of empty space in between. Now, this can be connected to my next immediate slide, where you are talking about scaling of galaxies. So if you now consider the Milky Way is of the size of 1 rupee coin. So one Milky Way's diameter given in the books is about 100,000 light years. Okay, 0.1 lakh light years or 100,000 light years. Find the distance at which the nearest galaxy is placed, and we know the nearest large galaxy is Andromeda galaxy, which is 2.2 million light years away, or 22 lakh light years away. So if the size of Milky Way is 1 lakh light year and the nearest galaxy is placed at 22 lakh light years, what it means is, if I take 1 rupee coin over here, 22 times the distance I will have to keep the next galaxy, which is very small. Okay, around a foot distance. Whereas within a galaxy, if you're looking at the position of the stars are really far off. So it means effectively a galaxy has a lot of empty space in between. And that gives them a good idea about, when they read something like the Andromeda galaxy is coming towards us, and another 3 billion years or 4 billion years, it is going to collide with our galaxy. It is not going to be collision between two balls, because the distance between galaxies is very small as compared to the size of the galaxy, but distance between stars is very large as compared to the size of the stars. So lot of empty space, and effectively the two galaxies are going to merge like a cloud rather than collide like a ball. So this can be of simple scaling calculations. Now you can also do calculation for scales at low temperatures. So what is the thermal energy of helium atom at room temperature? So you say energy is calculated as 3/2 kT, and you can then substitute the value of Boltzmann constant into the room temperature about 300 Kelvin, and then you get answer something like 6.21 × 10⁻21 joules. Okay, it is useful when you to convert these small energies into electron volt, and you get number something like 0.039 electron volt, because I've taken a factor of 3/2 over here. Okay, so it is like this. Many teachers surely must have remembered that KT is of the order of 25-26 milli electron volt, or 0.026 electron volt. So this is 1.5 times greater than that. Now, what is the momentum of such particles? So you apply momentum. Energy is basically kinetic energy, half mv square or p square by 2m, and then you can get a value of something like 9.1 into 10⁻24 kilogram meter per second. Now, typically when you are number crunching is one thing, fine, but when you are talking about momentum at atomic level, typically you get this number, 10⁻24 kilogram meter per second many times. So when you are doing a calculation, and when student has done calculation multiple times and he gets an answer of this order, then he should be comfortable. Okay, at least the order of magnitude seems correct. What next? What next is you can now calculate de Broglie wavelength, because they have been introduced to this concept of de Broglie wavelength. So the de Broglie wavelength, is h by p, and you have calculated momentum, and the value of h is known, and that turns out to be 0.73 angstrom, smaller than size of atom. I have purposely taken helium atom because then we are not talking about multiple atoms in a molecule. Simple atom, and this distance is very small. So typically in a gas, each of them are not going to interfere with each other, because the wavelengths are very small, and they are not going to basically interfere with each other. What happens at 1 Kelvin? So what you have done, temperature has gone down straight away by 300 times. okay, the value will reduce by 300 times. The thermal energy will reduce by 300 times. And de Broglie wavelength, okay, it will increase by a root of 300 times, but root of 300 is 17 times. So, and you get 13 angstrom. Now, 13 angstrom is very large as compared to size of atom. And if you're talking about 1 Kelvin, probably all helium atoms will be in liquid phase, or they will be close together. Okay, and if they're going to close together, the wave functions are going to overlap, and then it will become a single quantum system. So whether I should deal with the classical physics, or should I deal with quantum mechanics? No, de Broglie wavelength ruling. So when the size or the distance between two particles is comparable to the de Broglie wavelength, then quantum mechanics is required. If it is, the distance is large as compared to de Broglie wavelength, the classical physics is good enough. So that idea can be given with these kind of numbers. One additional problem on this kind of category. So when a star is compressed, okay, the ultimate end phase of many large stars is, people learn, that is neutron star. So where all electrons and protons are pushed together to form neutrons. And the size of a nucleus, student has learned, is about 10⁻⁻15 meters. Mass of neutron is same as mass of hydrogen atom, approximately this. So you can approximately calculate what is the density. So density is of the order of 10⁻18 kilogram per meter cube, which should be meter cube. Okay. And then typical mass of neutron star is expected to be a few times mass of the sun. So generally it is given that if the core of the star is more than 1.4 times mass of the sun, Chandrasekhar limit, then it will become a neutron star. And it can't be more than about 3 to 5 times solar mass, otherwise it will become a black hole, the core of a star, when it is going to die. So it is just few times mass of the sun. So mass of the sun, we know, is 2 into 10⁻30. So order of magnitude, let me just take that. And then when you take a cube root of this, because this ratio 10⁻30 mass upon density will give you volume, cube root of that will approximately give you the size. And that size turns out to be 10⁻4 meters, which is about 10 kilometers. So you see the neutron star typically will be of this order. You can do further inquiry into this, that when the star compresses by this much volume, and star is already rotating, like sun is also rotating. Sun takes about 25 days to go around itself. That angular momentum has to be conserved if it is not taken by other objects when the star is dying. So in that case, how fast it will start rotating, because that everybody talks about when things compresses, they spin faster. Okay, those conservation of angular momentum things we always talk about. We always talk about the rotating table experiments. Okay, but here we have got something huge system which is falling down by 5 orders of magnitude. So radius, when comes down to by 10⁵ times, the moment of inertia will reduce by 10⁻10 times, and therefore the angular velocity will increase by 10⁻10 times. And then we can do calculation. 1 day is of the order of 10⁵ seconds, and typically sun-like star is rotating with something like 25 days. Okay, so it is about 2.5 into 10⁻⁶ seconds, and now it is falling down by 10⁻10 times. So 10⁻⁶ divided by 10⁻10, okay, that will effectively give you milliseconds. So you see, the millisecond will be the typical time scale with which these neutron stars will rotate, and that is what you have observed in case of pulsars. The pulsars emit at milliseconds. So many times their rate of rotation is in the order of millisecond. So these ideas can be conveyed. The idea here is many of these calculations do not need very high level physics, and this can student can get a confidence saying that if I do these kind of calculations, I may be able to handle some big problems. I don't need to really learn a lot of theory for that, because this is a different kind of skill. Of course, there is always a question of a question where whatever I do, is it a correct thing to apply, or I mean, is some different physics involved? So it is perfectly fine that you may apply at times wrong way. Okay, but unless until we work on these kind of things, it is generally going to be students will not be able to develop the skill. The whole idea of learning is make a mistake, and there will be people who will guide you. The same thing is applicable for teachers. At times, there could be some amount of calculation mistakes can be very done, but conceptual, sometimes some conceptual problems can come, but slowly the confidence starts building. Now here comes one or two surprising answers. So I'll just end with those. So suppose you compare this. This is actually a problem from Halliday and Resnick, comparing force on moon by Earth and Sun. So there is no estimation here. It is a straightforward comparison, but it gives surprising answers. The answer to the problem can lead to further inquiry. So say, what pulls the moon with greater force, the sun or the Earth? So the sun-moon force, we know we are applying law of gravity. So G into mass of the sun into mass of the moon upon moon-sun distance square. Now moon-sun distance is approximately same as Earth-sun distance, and then moon-earth distance, moon-earth force, okay, is G into mass of moon, mass of Earth upon the distance between Earth moon square. And then you see, when you want to take a ratio, the common factors will get cancelled, and then the moon sun force upon moon earth force will be given based on this factor. Now you can put the numbers, and what you get is interesting number 2.2. What is this? The force on moon by the sun to force on moon by earth is approximately double. So sun pulls the moon with almost double the force than earth is pulling the moon. And then the inquiry can start, and then why moon is not going around the sun? And then you start saying, but moon does go around the sun. Okay, then what could be the orbit? And such kind of questions can be asked. I'm ending with this last example where I have purposely written this, okay, that expansion of the universe wrongly applied at a smaller scale. This also is an interesting calculation. Okay, the results are surprising. So Hubble's law suggests that universe expands at 72 km per second per megaparsec. Okay, so if object is at 1 megaparsec distance, it seems to be going away at 72 km per second. If it is at 10 megaparsec, it is going away with 720 km per second, and so on. Now, parsec is approximately 2 lakh astronomical unit. In fact, by definition, it is the tan of 1 arc second reciprocal. So it is 206265. And then 72 km per megaparsec. If I want per parsec, then I have to divide by mega, that is a million. So kilometer divided by million becomes millimeter. Okay, and then 72 millimeter per second per parsec. And if I want to convert that into per AU, per astronomical unit, it is I have to divide by this 2 lakh. So I know 1 second, 10⁵ second is 1 day approximately. So basically, it is ultimately it will get converted into 36 millimeter per day per astronomical unit. Okay, so if an object is at 1 astronomical unit, the thing should move away at 36 millimeter per day. That means Earth should go away from the sun at 36 millimeter or 4 centimeter per day. That doesn't happen. Okay, but moon is about 1/380 astronomical unit, and there are about same number of days in a year. So moon must go away by about 30 to 40 millimeter per year, or 3 to 4 centimeter per year. And this is almost the rate at which moon is going away. So you see, now this is wrongly applied, but moon goes away for a completely different reason. We say that Hubble's law is not applicable at such small scale, but out of interest, if you do these kind of calculation and it turns out that, oh, you are getting the correct answer, but by wrong assumption. So such things also happen. And these things, I'm sure, gives good confidence to teachers when you're trying out new things. Okay, and then of course there are teacher groups where you can interact with these kind of questions, and ultimately the discussion among the teachers for applying new ideas also should happen. So that is where I end my session. Thank you.
Okay, so can I take some question from the chat box? Yeah, there is one question asked by Mr. Vikram Verma. Please explain the conversion of power of temperature from power 4 to 2.
That was a typo error which I corrected.
I can't see any more question in the chat box. So thank you so much, sir, for sharing your wide spectrum of knowledge and enlightening the audience with such a wonderful lecture by putting a lot of examples, real life example, I can say. So thank you so much, sir, for giving your precious time to us. Now, I invite one of our very active member of IAPT, Dr. S.K. Singhal, PGT Physics, MIT International School, Mayur Vihar. And he's also holding the post of Treasurer IAPT RC-1. So welcome, Dr. S.K. Singhal, sir. And he will
Thank
talk
you, sir.
innovative experiment. And meanwhile, I request the participants of RC-IEP to be ready for the presentation as we begin the competition just after this innovative experiment session.
Thank you, Yogesh, sir.
It's all yours.
Thank you, sir. Very good morning to all of you. Seema ma'am, Mahesh sir, Sejwani sir, and all participants. Today I am showing you some innovative experiment. I tried to record some videos, but not able to record all, but few I have recorded because the video are so heavy. So I'm trying to show you the videos. So we are today doing the innovative method of teaching physics by low cost, things, because when we go to the class, it is not necessary every time we have the apparatus with us. So I have designed some experiment which can be performed in the class, which can be shown to the student in the class. And also I have taken few videos that I will show you later on, which we have taken from the NAST exam that was conducted by Anveshika. So I will show you one by one. So the concept is that when we say I hear, I forget, and I see, I remember, but I understand. So whenever we do an activity, then only we remember all these things. So first activity that I'm going to show you today, that is the motion of charged particle in electric and magnetic field. So what we show, because we teach in the class that when a charged particle enters the magnetic field, the force is acting. When it moves the electric field, that is equal to QE, the force is acting. And we also teach in the class that when the charged particle enters in a region where electric field and magnetic field both exist together, then it describes a path that we show in this small activity. You can see. So what are things required for this activity? Battery eliminator, battery dish, aluminum foil, chalk powder, connecting wire, ring magnet, crocodile clip, water, and few salt. And this is the video I am showing you that I have recorded. You see in the lab, in which first thing, this is the battery dish you can see, and a ring magnet you can see we have in this video. What is required? What else is required? You can see the apparatus. This is the battery dish, and this is the aluminum foil that we put here. Make this arrangement. Take this one electrode here. Right. So now we have one electrode here, and now we have got some water in it. Now you can see connected one end to the battery eliminator, and another one we put at the center. We put at the center of this ring magnet. Yes. Now you can see this all chalk powder, and we have small salt start moving on this circular path You can see the arrangement. This is the battery elementer. We have connected 6-volt battery, ring magnet, and you can see the charge part is moving a circular path, just like we taught in the class that a charge particle enters in a perpendicular magnetic field. It acquires circular path. We teach cyclotron. Same thing you can see here. The particles that we have taken small sort because the ions are there. So there is a magnetic field because the ring magnet is kept below this battery dish. So there is a perpendicular magnetic field. And electric field is also, by applying the 2 electrode, one we have connected near the boundary of battery dish. Another we have kept at the center. This is the electric field is applied between the 2 points, and magnetic field is there. So electric field accelerates the charge particle, and magnetic field providing the circular path. So the charge particle continue to move. Now you can see if we use the salt, if we talk about the salt, it has the NaCl, Na ion, and Cl ion, both the positive and negative ion, but both are moving in the same direction. Because if we see the positive charge and negative charge, both we have, but we see the magnetic field is in the same direction. Acting on it. Yes. So magnetic field is acting same direction. Electric field you can see is applied over it. So force is acting on the both positive and negative charge particle, but due to the motion, because if one we say the positive charge particle moving forward, so negative means the current is taken opposite, but the motion is means the direction of force on the electric field is also different. That's why they all are moving the same direction. This small activity that we can show to demonstrate how the Lorentz force is there. Lorentz force is acting. Somebody has raised a hand. Yes, ma'am. Yes. Yes. Satish sir, do you want to say something?
Yeah, Satish sir has raised the hand.
Yes, sir. Yes, sir. Any question? Sir, I'm not able to hear you.
Sir, your voice is not clear.
I think by mistake.
Tell him to type it, whatever query he has.
Yeah.
And
Yeah.
mute him.
Sir, can you write in the chat box?
Yes. Single sir, you continue with your talk.
Okay. So we continue with the next activity. Now the second activity is the static electricity. We teach in the class about the electricity by static electricity. Electricity is by when we rub a body with another body, the charge is acquired by the two bodies. Equal and opposite kind of charge are acquired by the two bodies. So here we can show you small activity in which we can demonstrate. And one more important thing is that when we rub the two bodies, not necessarily the body to be conducting. If we have insulating body, then also we can show the static electricity. So what activity I am showing you, I have taken the plastic thread of the atta bag, generally the atta bag that we have from market, from where I have taken this threads. Okay, it's the video. Just the video here.
Sir, there is no audio in your video. Can you?
Single sir, can you hear us?
Sir, your video is not audible. Single sir, can you hear us?
Yogesh, I'm calling him.
Yes, ma'am.
He's rectifying it, right?
Yeah. His audio is off, ma'am.
Sir, your audio is off. कर दे, वो ठीक कर देंगे अभी.
So can you on your audio?
Now I think I'm audible to now.
So you're audible, but your video is not audible to us.
Yeah, video is not audible. Video is I'm
yes, putting
what is there. So threads that I have taken here, you can see I'm rubbing with the hand these threads. You can see I'm rubbing this. I rub this thread with the hand. So by rubbing, the charge is acquired. You can see there is no audio in the video. I am just telling you. So when I rub this thread by hand, this is the PVC threads. Rubbing with the hand, charge are acquired by all the threads. You can see now they start repelling because they acquire the charge. This is because this charging takes place now. After charging, they start repelling each other. And now thing is that now when I bring my hand, it will start attracting because the charge on my hand and the thread are of opposite kind. But thing is that when I touch the thread, it is not neutralizing the thread. It is not neutralizing the thread. Why it is not neutralizing? Because the static charge, the point at which I touching the thread, only that point is neutralized. But the charge remains on the other part of the thread. If I want to neutralize the entire thread, I have to touch the thread at all the points. You can see this video. It is attracting now. You see how will I utilize the complete thread. This is the one point is attracting because both hand and the thread having opposite kind of charge. When we touch, you can see now touching this thread to all the points. All the points. Now that particular thread will be completely neutralized. Now you can see there is no attraction with the hand thread. Other will attract because I have neutralized only one thread. So charge, this is the charge on this insulator PVC thread, and other you can see other one attracting as we bring the hand. They all are attracting as it is. Only the one thread at which the charge removed throughout is does not attract. So the concept is that the charge can be given to the insulators also. The static charge is given, and the static charge remains there. It is not flowing, and to remove all the charge, we have to neutralize the complete thread. This is another activity that can be shown easily in the class. So now we are coming to the next activity. See, this is a very interesting activity in which we will show by using a scale, meter scale, and we put 2 fingers below. I'm just showing you a small video. Just I'm showing you. Yes, you can see I have this scale and I'm moving the fingers on the 2 sides. There are 2 things. Either I will keep this finger on the two ends and start moving toward the center, or I put the finger in between and then move away from this case. So what is there in this case? What we found when we try to move this, you can also see I have this also at this time. You can see here also I'm showing you. So when I put one finger can move easily, but another finger does not move. Can anybody suggest why? The same scale, I have two fingers. I have kept at equal distance initially. When I start moving, then one finger is moving very quickly. Another one, I'm not able to move it. What will the reason for this? We have same scale and same type of finger I have, but one finger is moving, very easily, and another one is not. Satish sir again raise the hand. Sir, do you want to say something? Yes, sir.
Hello.
Yes, sir. Yes, sir.
Sir, I would like to try its answer.
Yes, sir.
That as you can observe that both the two fingers do not move simultaneously.
Yes, sir.
Only one finger move at a time.
Yes, yes.
That is due to the reason that when one finger moves, the other finger, which is in touch with the scale, provides friction force as a normal reaction. As a normal reaction.
F is equal to B into R.
Yes, sir. Normal reaction to the force which is given just to provide other finger move. Normal reaction is, it doesn't mean that it is just providing it. The word is not normal reaction. This is just a reaction. मैं हिंदी में बोलता हूँ थोड़ा सा और ज्यादा क्लियर हो जाएगा कि जैसे एक फिंगर जैसे मूव करती है तो दूसरी फिंगर तभी मूव करेगी जब उसको कोई पीछे से रोकेगा. रोकने वाली दूसरी फिंगर है, बी फिंगर है, वो रोक रही है, तभी पहली वाली फिंगर मूव कर रही है रिलेटिव मोशन में. और जैसे ही पहली वाली फिंगर ए फिंगर जो है वो थोड़ा सा क्रॉस कर जाती है सेंटर ऑफ इसका जो मूवमेंट्स है, मूवमेंट ऑफ इनर्शिया जो है किसी एक पॉइंट पर वो एक तरफ ज्यादा हो जाता है, तो वो उस तरफ वेट ज्यादा हो जाता है, उस तरफ नॉर्मल रिएक्शन ज्यादा होती है इस टाइम. और बी वाली जो है वो अब वहां पर उसका नॉर्मल जो रिएक्शन है, मूवमेंट ऑफ इनर्शिया मूवमेंट है वो कम हो जाता है. जिस तरफ वेट ज्यादा हो जाएगा उस तरफ मूवमेंट ज्यादा हो जाएगा. इस कारण क्या है, वो उस टाइम वहां पर फ्रिक्शन बढ़ जाएगा, तो बी फिंगर है वो मूव करना शुरू करेगी. मींस दोनों एक दूसरे को बैलेंस करती जाएंगी, एक दूसरे की नॉर्मल रिएक्शन. अब यहाँ पर नॉर्मल रिएक्शन की बात कर रहे हैं, पेपर पे थोड़ा करके दिखाएं तो बेटर रहेगा इसको.
जी सर, आप ठीक कह रहे हैं सर. इसमें एक्चुअली क्या है, फोर्स ऑफ फ्रिक्शन दैट वी नो इज म्यू इनटू आर. So when we start moving the finger, when one finger move, that time the distance from the center to the first finger and second finger is different, and that because this entire scale is balanced, so torque, that is moment of force, is same, not moment of inertia. Moment of force is same, that is reaction into distance. As the distance is more, then reaction is less. And reaction is less means friction is less. So that means friction on both the fingers are not equal. The finger that is away, have more friction, and the finger that is coming just close have the less friction. That's why we are able to move the one finger very quickly, and another finger we are not able to move that. And as you say, the center of gravity is there, and we measure the distance from center, and then due to this different value of reaction on the two fingers, there is a difficulty in moving one finger is when we are moving another finger at the time. So simultaneously it is difficult to move both the fingers. Right, so that this is the thing that we can show to the student. On the board also you can teach them when we teach the balancing the rotational equilibrium. When we teach in the class, that time we can show this activity in the class by using a scale. Just a small activity I am showing you. Another activity that I have, see, there are many things that we have. I have taken, because I have not recorded many activities here. I have taken one activities NAST also. I'm showing you. This is the video I have taken from there. You can see this video here. Okay. Okay, don't no problem. You can see we are cutting this guava by this knife into equal parts, right? As that was shown in the video. And what is there? Question you can see. Yes. Question I have taken from NST. Assume that knife divide the guava equally into parts with the cutting operation. Before guava separate, the resulting force of the guava is zero. The direction of movement of knife opposite to the direction of motion of knife, perpendicular to the motion of knife. So we are applying a force. Generally, we say when we apply the force downward, there is a net force acting on it. But here there is no net force acting. Can anybody explain why? Why there is no net force? Okay, you can see when we apply a force, the guava to cut into equal part, centrum of the guava remains fixed during this cutting operation. So the acceleration of central mass is zero. So by Newton's second law, the resultant force of the guava is zero during the cutting operation. The downward force applied by the knife of the guava is balanced by the reaction from the ground. That's why net force is zero. And horizontal force applied by the two parts are equal and opposite to do symmetrical cut. So that's why the net force is zero. Yes. Although it appears that we are cutting the guava, so we are applying a force. Another activity also, taking the recorded. In this activity, what we do, we have a cardboard, put it with the two chimney. Convection current is set up when the lighted candle is placed below the one of the chimney. In the place of chimney, we can put two tubes. We can see the movement of air by using smoke. We can use a dhupbatti agarbatti. This experiment is explain the reason behind the convection current. The pressure and air density at the point A, B, C, D are analyzed. You can see this is the experimental setup here. For this, we need the apparatus. We have a cardboard box, and these two tubes are fitted here. And what we do, we just put in a burning candle here, and we use smoke. So what we observe. Okay. This video also will not run because last moment one system does not work, so I have copied the PPT in the other one. So I think the link is not there. So what is there? We will just put a candle here and put the candle, and we are using the smoke here. So what we observe, the the smoke that is coming out from here. Here for the smoke is coming out, and there is a movement of smoke from this side also. So smoke is coming out here. That is the convection current that is showing here because the temperature is high. And now the question that I want to ask you, the pressure of air at the point A, B, C, D are PA, PB, BC, BD. The air density at these points are Rho A, Rho B, Rho C, and Rho D. So which one is correct? At which point you can see again? You can see the point A, B, C, D. A and D are in the same test tube, same tube, and the candle is kept below A. Another tube we have BC, that is, the candle is not there, but smoke we have produced inside it. So the question is, at which point the pressure is equal? PA is greater than PD, or PB greater than PC, or PA greater than PB, or PB greater than P. So at which point? That is very clear to all of you. Anybody want to give the answer? You can see. So the point A where we keep the candle. So the point is this place is hot. So air from point A start moving toward B, and at the same time, the air from B starting moving towards A. So you can see the rise in temperature. It is the speed of the air molecule. So increase the air pressure and decrease the air density. Point C and D are exposed to the atmosphere. You can see the diagram also. Pressure at this point will be approximately equal to atmospheric pressure. But outside the box, so air start rising from A to D because A is heated to the pressure difference. So to fill the gap at A, the air point B rushes to point A. So the movement of air from B decrease the pressure at B. So air start moving from C to B, pressure difference, and this process set up a convection current, which air moves from A to B and C to B in a cycle. So very clear, you can see, because when we say the air move from high to low pressure, you can see at which point the pressure is more. Yes, because it is moving from B to A, so pressure at B is high. It is moving from A to D, pressure at A is higher than D. Pressure at A higher than D. So that for this activity you have to bring the student in the lab. One more activity I want to show you. So what is there? There is a spring which is hanged, and there is a weighing machine is kept to it. And what we observe, as the spring oscillates, the reading of weighing machine keeps on changing. I'm trying to open the video system. The reading of weighing machine keeps on changing. So can anyone give the reason why the reading of weighing machine keeps on changing when we are, let's see. Slinky oscillate on the weighing machine, the reading of weighing machine changing. Give reason. Acceleration of slinky exert extra force on suspension. Weighing machine affects or repel the moving slinky. The mass of slinky depends on motion. As the distance of slinky from the earth center changes during oscillation, the gravitational force on it changes. I'm just opening the video also. But it is clear to you whenever the slinky oscillates, they compress and extension is there. So during that time, why does the reading of weighing machine changes? Okay. You can see the acceleration of slinky exert whenever when we move down, then the acceleration is there. Upward, the upward acceleration. The acceleration exerts an extra force on this point of suspension, due to which the reading of the weighing machine changes. Sorry, I could not show you the video. Just trying to system if it can work. In my system, suddenly update starts. That's why it stops every time. Okay, meantime, I'm showing you another question. Here again, you can see we have a slinky in my hand, and it oscillates. When I, when I release it, slinky gets compressed in the particular way. The video shows the upper end and coming end. Yogesh sir, can you open my video of the another device?
Sir, have you shared the link or?
That I have already joined.
I have made you co-host.
Okay,
You can
okay.
go ahead.
Okay, it is there.
Yes.
Yes. You can see the video. I think now able to see this video. From beginning, I'm showing you. Now I keep this slinky on the weighing machine. It is stationary now. When it start oscillating, you can see the reading is constant. Now reading keeps on changing. Right. So that I already discussed that region is okay. Yes. So here it is very clear that accelerating slinky exert an extra force on the suspension. That's why reading keeps on changing. Next thing that I want to show you that video. You can see this video now. And observe it, and we drop it. See what happened. When we release, the slinky gets compressed. During the free fall, the slinky gets compressed in a particular way. The video you can see the upper end coming down fast, whereas the lower end almost remains stationary. After initial compression, the slinky fall down in the compressed form. So the reason is that the slinky swings during the fall because it becomes massless during fall. Both earth stop pulling it during fall. The slinky pulls the upper coil in the upward direction, but the lower coil in the downward direction. The slinky pulls in the upper coil in the downward direction and lower coil in the upward direction. Right. So many questions can be raised from the student, and we can ask the student what is the answer for that after showing this activity. So it is very clear. You can see this because at the upper end, the weight is acting downward and the reaction is also acting downwards. Both F and mg are downward. And this lower end, you can see the force, weight is the downward and reaction is upward. That means the force at the upper end is more as compared to the force at the lower end. That's why, it remains, it appears to be stationary, and upper end is coming down because the net force on the downward direction is mg plus fu, and there is a downward acceleration acting on the spring. That's why this type of motion is observed. Otherwise, generally the answer what we say, it is falling freely under gravity. You can see the answer. The most the students giving the answer like that. It becomes massless. It is not massless, but you can see the force acting on the two ends. The upper end, the force will be downward. Net force is downward. That is more as compared to the force acting on the lower end. You can see here also the upward force, downward weight. This one at rest it is mg, but when we release, it is acceleration. That is, you can see because the upward force is more, and downward and the lower point, F and mg are acting in opposite direction. So acceleration is given by the resultant of n. So that's why the spring gets compressed. Another activity I'm just showing you. This is also a very good activity. The water is coming out from this tap, and we have observed 2 points A and B. See this video. See, these videos I have taken from NAST screening test. Water is coming, and there are 2 points A and B. Observe the video carefully. So what we have to see in this video, is there any pressure difference at the point A and B or not? Just one minute. Yes. The water is falling down the stream from a tap, the point A and B at the center of the water stream. Point A is height h above the point B. Pressure at A and B are P and PV respectively. The flow speed at these points are BA and BB. The density of water is rho. So which one is the correct? Is the pressure at point A and B equal, or pressure at B is more, pressure at A is more? You can see the 4 choices we are given here. Pressure at B is less than pressure at A plus rho GH. Pressure at B is equal to pressure A plus rho GH. And velocity of B is equal to velocity of A. Velocity of B is more than velocity of A. So which thing that is observed very clearly in the video? Any one of you can tell? The video that we have seen, the water is coming out from the tap, and if you have observed clearly, one thing comes that as we come down, you can see this one. This is the flow. Okay. You can see this is the type. The area at the upper end and the area at the lower point is less as compared to, you can see in this way. And we know the equation of continuity, the area is large, then velocity will be less, A into V is constant. Here the area is less, so velocity will be more. So large area, small velocity, small area, large velocity. And if we use Bernoulli's theorem, P plus half rho v square is equal to constant. So the point at which the velocity is large, the pressure will be less, because P plus half rho v square is constant. So there is a high velocity, there is a low pressure at point B, and high pressure at point A. So there is a difference in the pressure at the 2 points. That's why, pressure at B. And what is the difference? If we put this, in this formula of Bernoulli's theorem, PA plus half rho v square plus rho GH is equal to PB plus half rho v square. So we will come to know that PB is equal to PA plus rho GH minus half rho VB square minus VA square at VB is more greater than VA. So we can say the pressure at B is less than PA plus rho GH. And if it is fluid is static only, then only we can say it is equal to that. PV is equal to PA plus rho GH, because otherwise it is moving, so velocity at the 2 points will be different. So we have to consider for the VB square minus VA square also. So otherwise, generally we say that both the points are in the atmosphere, so pressure at A and B should be equal. But here the pressure at A and B are different. I'm just showing the last view that I could not show you. Now the system is opened, so I can show you that video also. Yes. That is the video that I was showing you. This is the video that I could not show you that time. Just put this is a box only. Just put this candle, and this is the put smoke. We put it here. It's coming up. It is coming in from this side, because the pressure at this point is A is less as compared to the pressure at B, to the high temperature. So air moves from B to A, that is coming up, and similarly as the air from B moving to A, there is a the air now there is a less density, so the air from point C start moving to point B, and this B to A and A to B. So that was the thing that can be used to explain this concept of the convection current. So now coming back to the this video also, I'm just showing that because I could not show you now. Cutting of power. So here that was shown to you. That time net force is 0, although it appears that force is acting in normal direction, because the force is equal to normal reaction of the ground. So that's why net force is 0. Okay. Anything any one of you want to ask? So I'll just show you, because I could not show you many of the video that I want to show you, but I try to show you some videos that I have recorded and some I have taken. So anybody want to ask? The purpose is only that how can we make our class interesting? How can we teach the student by using small activities in the class? Not necessarily every time we have apparatus to show the experiment, but thing is that we can make our class interesting. So thank you to all of you. Any question if you have? Any
Yes, sir.
question?
There are some question in the chat box. If you can
Yes,
read,
sir. Yes, yes.
I can read it for you. Mr. Aditya Sagar asked that the force will be zero as the guava deformed while being cut, and some of the force is being used in that.
Pardon, sir. The force on the guava is 0.
The force will be zero as the guava deformed while being cut, and some of the force is being used in that.
Yes, the force is there, but the net force that we talk about, because as the reaction is also there, the net force on the guava is 0. Net force is 0. We are not talking about the pressure. You see, Monu sir is saying always pressure. They are applying a force and to cut the guava. But the net force, if we talk, because when we apply the force, then you know, the reaction is there. So net force is 0. The question was there, when we cut the guava, are we applying a net force on that or not?
Yes, I think he has got his
And
answer.
any other question?
Yeah, next question asked by Mr. Satish. Sir, can you unmute yourself because you have asked the questions, and directly you may ask your question if you have.
Yes, sir. Yes, I think we have asked any other question we can ask.
Satish, sir?
Meanwhile, Yogesh, ask any other
Yeah.
question if there is any.
Yeah, man, there is no other question in the chat box. So let us thank
Fine.
the speaker. Acha, Satish sir,
Sir,
unmute.
saying, unmute me, please.
Yes, yes.
Saying
yes.
Thank you, Dr. Singhal.
Yes, sir, I have unmuted
Thank-
you. So, sir, you can ask now.
Thank you, sir. Good presentation.
Thank you, sir. Actually, what happened, my system in which all PPT was there was crashed at the time, last moment, because there's some update was came. So I started with another system. So I could not show the many videos that I transferred at that time. But thank you for cooperation.
Nevertheless, it was good.
Satish sir, do you have any question?
Sir, unmute me, please. Yes,
Yeah,
sir.
I have already
Yes, sir.
unmuted. Yeah,
Yes, sir.
please.
Yes,
Sir, sir, in one activity, you were using circular magnet
Yeah, yeah.
and
Ring magnet, ring magnet was
yes, ring magnet, and in that the chalk particles starts moving.
Yeah.
Yeah. Very good.
Some salt
activity.
was also used. Some salt
Yes,
was also
yes,
used. in
yes,
this.
sir. But that was the face of the magnet that was using was something North Pole or South Pole.
Maybe anyone, no matter. for me.
Anyone,
No matter. But the magnetic field of that magnet is not exactly in the upward direction. That was just like a toroidal magnet. That was just like a magnetic field of a toroid.
Okay.
In
In toroid
that
also,
case,
if we have circle, if we have any coil, we have
yes,
the
sir.
magnetic field along the axis.
Yes, sir.
If we have toroid or solenoid,
Yeah.
then the magnetic field is along the axis. So it is along axial when we use this one. So it may be upward or downward depending on which pole of the magnet was kept.
Okay.
So
That I
magnetic
want to
field was
ask.
there. Yes, sir.
That I want to ask that in a general, when we do this experiment, we use a North Pole or both the poles, North Pole, South Pole, so that the perpendicular, exactly straight perpendicular magnetic field acts on those
Sir,
particles.
Yes, sir. You can perform that because I performed this many times in the class.
Yes,
So once I used the horseshoe magnet also, but at that time the motion was not observed so good because the magnetic field of this horseshoe magnet is weak. We need a strong magnet. If you have any strong magnet, that is the horseshoe type magnet, you can do it. The thing is
Okay,
only
sir.
that we should use a strong magnetic field, so that the appropriate force will be there to
Okay,
move
sir.
this charged particle there.
Okay,
Can
sir.
I also speak?
Thank you, sir.
Yes, sir.
Singhal Sahab, can I also speak?
Yes, sir.
Please, please, sir.
Mr. Satish, I think was talking
Yes, sir.
about.
Yes, sir.
Mr. Satish, actually, you are talking about the direction of the force will not be perpendicular. It is a toroidal, but that is
Yes,
not
sir.
true. In this particular case, which was shown by the Dr. Singhal, is that is not the case because the particles were kept very close to the poles of the magnet, and since they were very close to the pole of the magnet, therefore all the lines are supposed to be nearly parallel, and when they are parallel, they are perpendicular to the face.
Okay,
So
sir.
there, so that problem is not a big problem. It is not actually toroidal. Of course, if you keep the this
Yes.
depth of the water very large,
Large.
then of course it will not be perpendicular to it.
Yes, sir.
Okay, if there is no more question, then let us thank the speaker. Thank you, sir, for demonstrating beautiful experiment and providing your valuable time to us. Thank you so much, sir.
Thank you.
Now we have next session, regional for innovative experiment in physics. So the judges for the competition are Professor Y.K. Vijay, our innovation professor, director, Center for Innovation in Science Teaching, IIS, deemed to be University, Jaipur. Sir, I welcome you. And our next judge, Professor H.K. Sehjwani, Professor Dean Academics, IEC, College of Engineering and Technology, Greater Noida. So our first participant here is Miss Sagar, PGT Physics, Bharatiya Vidya Bhavan Mehta Vidyalaya, and her title is Motion of Charged Particle in a Uniform Magnetic Field. So, ma'am, you can share your screen. Start your presentation. Anu Sagar is here. Okay. So for time being, let us call to another speaker. I hope she will join shortly. Our next speaker is Prem Kumari Narang, PGT Physics, MIT International School, Mayur Vihar. And she will talk about to measure the speed of light using chocolate bar.
Sir, I think she told she will do sometime, from the time late करने के लिए she requested me.
Okay.
उनका आप बाद में कर दीजिए.
Okay, okay. So let us call to our next speaker, Mr. Jaswant Kumar. Jaswant sir, are you here? Yes. So Dr. Jaswant Kumar is from Central University of Haryana, and he will talk about do it yourself solar radio telescope. So Jaswant sir, mic is yours now. You can present and share your screen.
Thank you very much, Dr. Yogesh. Am I audible?
Yes, sir. Yes, you're perfectly audible.
Okay, thank you very much. Okay, thank you very much. So I would like to begin first by thanking all the organizers of this IAPT symposium for inviting me and for sharing the information with all and sundry on social media, on WhatsApp, so that people like me who are not really getting the information, who are not really member of IAPT, we can still join. So I'm very much thankful. I'm especially thankful to Dr. Yogesh and Dr. Poonam, because they are also the people who helped me in finding my teaching job when I was searching for it just after my return from the postdoctoral stint. So yes, it's a really a pleasure to be here and present some of present a type of experiment that I have been involved. And the experiment has purely been carried out by my students. Okay, so the credit, if it is anywhere due, it is all due to the students, and I really do not deserve any credit for the experiment that I'm going to present. So before I begin, I would also like to inform all the honorable members that I am a student and teacher of physics at Central University of Haryana. This is situated in a place which is near Mahendragarh, which is one of the districts in the state of Haryana. So I start. Just a moment. Yes. So can you see my screen, please? Can you please tell me?
Yes, sir. Yes.
Okay. Thank you, Manoj. So yes. So what we are going to discuss is that we are going to discuss a small radio telescope. Okay, and this telescope has been made using a dish antenna. All of us, okay, especially the students, we have been fascinated by something called the optical telescope. Okay, we are fascinated when we see the moon closely. We are fascinated by it when we see the rings of the Saturn, and when we see other planets from the optical telescope. We are very much fascinated by it. Radio telescopes, on the other hand, they are not so popular among the school and college students. Okay. However, radio telescopes are one of the astronomical devices which are used to get the observations from as far as the center of galaxies, from as far as the black holes which are situated at the center of galaxies, and so on. Radio waves, they are useful because their wavelength is comparatively more than the wavelength of the light. Okay, because of which they carry small energy, and objects which carry small energy can traverse a long distance compared to the objects which carry large energy. Because if something carries large energy, it also dissipates, it also loses its energy faster. So radio waves that way are very helpful for us in knowing about the universe at long distances. I would also like to, okay, so this I think I've explained. So I would like to be very brief and tell you some of the comparisons which are between visible and other electromagnetic wave spectrum that we get for the objects in the heaven. So these pictures that you see, these pictures have been taken at sensitivities of the picture. One of the picture is taken in visible band. Some of the pictures have been taken in infrared band. Some of the pictures have been taken in radio band, and so on. So what you see is that we can explore different parts of an object by taking the image of the object in overall electromagnetic spectrum. The topic here is to make a radio telescope. So the credit for making the radio telescope goes to someone called Carl. He was a radio engineer who was working on communications in the United States at Bell Laboratories. And he is the person who is credited with invention of radio telescope in early 20th century. So what is a radio telescope? It's a sensitive radio receiver. It measures the intensity. Intensity you can define as power per unit area that we receive of the radio waves, and this is used to study naturally occurring radio lights from stars. It is also used to study radio lights from galaxies, from other objects that I initially informed. So the working principle on which the radio telescope works, they are very simple. So what they use is that they use something called a parabolic shaped disk. And this disk, what is the function of the disk? The function of this disk is that it reflects the radio waves to an antenna that is kept over this disk. The signal that we receive is then sent to an amplifier. This amplifier magnifies the signal, and then this magnified signal can even be seen on a screen. Okay. So how did we make a small, affordable? So this sounds so fancy, but then how do we get this thing to the classroom? Because the fancy radio telescopes that we have around the world, they cost huge amount of money, and it is not practical for us to make a visit to them and to demonstrate them in the classroom. So how do we form a small radio telescope that we can demonstrate to students and to general public in daily life? So for this, what we have used is that we have used a dish TV antenna. Okay, dish TV antennas, I think, are very popular. Almost every home in cities and villages these days is using one of these dish TV antennas. We can even use an antenna which is old. So that means you can also get it from scrapyard or something. So it costs less than 500 rupees if you get it from someplace. Then we use some coaxial cables, and there is a satellite finder which is available with almost all the cable TV operators. Okay, and you can buy it for some 200 or 300 rupees from Amazon. Okay, after this, if you like, you can use a set-top box. But even if you do not use a set-top box, these three things, they are the only essential parts of making a small radio telescope. So what I would like, this is the radio telescope that we made, okay, that we made at our school, and then we did some observations with this. So this is one of my students who is holding this satellite finder with him, and you can see some readings into it. So if you see closely, then one of the reading is showing 92%, one of it is showing 56%. So what it shows is these are like noise meters. Okay, what they show is how much signal are we getting from it. One more thing I would like to One more thing that I would like to describe about this telescope that we have made is that the frequency to which this TV antenna is like sensitive, this is in a band which is called KU band. So this band goes from 10 megahertz to 20 megahertz. So that means if there is a signal which is coming between 10 and 20 megahertz, then we can detect that kind of signal. The sun and the other geosynchronous satellites, they emit in this particular range. So that means this kind of antenna can be used to track some of the satellites that are going around the Earth. Okay, it can also be used to observe sun. In addition to sun and the satellites, there are various things which emit in radio wavelengths. So that means you can also observe it to find. So for example, human body also, some of the wavelengths, some of the radiation that it emits, this is also in radio. So you can use these antennas to detect the presence of foreign objects and so on. So it's kind of very interesting, and it can appeal to the student. Not only this, in this small investment of less than 1,000 rupees, it can give exposure to the space physics or the space astronomy that people are trying to do. Okay. So what we do, since this is in KU band, that means since this is in 10 to 20 megahertz band, we connect the dish TV antenna with the help of coaxial cables to the satellite finder. And then means the simplest thing that you need to do is that you just need to point this antenna to the object of interest. So suppose you want to observe, so before pointing it to the point of interest, you can also calibrate the satellite finder. because there will be some default reading that will be coming, the default reading of noise that will be coming in the satellite finder. Okay, even when you point it inside a direction in which there are no radio emitting sources. Okay, so that is called the background noise. So you can first calibrate the satellite finder with the background noise, and then can point the dish TV antenna to the object of your interest, and then see how the reading in the satellite finder changes from the reading that it was showing when you were trying to calibrate it. Okay, so this kind of hands-on activity, I think this will be very fascinating for the students when they do something for themselves. That means when they observe that they are getting some radiation and the readings in the satellite finder, they are increasing. So I think they will be very much motivated to learn more and more about these astronomical objects. The final radio astronomy that we do with large radio telescope uses the same principle which have been used in this small affordable radio telescope. Okay, so one of my students, he did all these experiments. So what he did was that he took this antenna near a mobile tower. Okay, I will show you the table when he observed different observations. So he took, because this is a handheld antenna. Okay, you can just take it, means you can just hold it in your hand and take it to the place that is of your interest. So he took this antenna near a mobile tower. He observed it. Okay, then he observed it. Then he pointed his antenna towards the sun and then observed the readings of the satellite finder once again. What he did was that on the internet, we have information about the placement of GSAT satellites. Okay, GSAT satellites are these geosynchronous satellites that are like in an orbit around the Earth. Okay, so their azimuthal and inclination. So that means the distance above the horizon of these satellites is available. Okay, so what you can do is you can now, because this is like a trial and error game, so you can now point your dish antenna towards these GSAT telescopes, GSAT satellites, and then try to see what kind of radiations we are getting. Sometimes what can happen is that the satellite position and the position of the sun may be in the same direction. So you might think that it is difficult for you to differentiate whether the radiation that is coming, whether that is coming from the satellite or whether that is coming from the sun. So small bit of physics, which is called the polarization of electromagnetic rays, it can help us differentiate the radiation that is coming from sun and coming from satellite. For example, we know that the electromagnetic radiation that we receive from the sun, this is polarized in all directions. So that means this is called unpolarized light. Whereas the radio light, the radio radiation that we get from these GSAT satellites, that is like linearly polarized. So if you try to rotate this antenna and you still get the signal, then that means the signal is originating from sun. If you get it only in one particular direction and then the strength of the signal changes as you change the rotation of the antenna, then that means that signal was coming from one of the geosynchronous satellites. So this was one of the activity that we performed, and these are some of the readings. Okay, when the student was doing the project, as I told you earlier, there are these interesting satellites, for example, INSAT 3A, 4B, 2A, 3B, and some of these satellites, their azimuth and elevation. I tried to tell you, azimuth and elevation are like theta and phi. Okay, they are like the coordinates of an object in the sky. So these coordinates you can set from your place, and then you can point your antenna along this direction. So these directions are with respect to the north. from your place. Okay, so then you can make this antenna and then do all these observations. So I would like to conclude by telling you that we made an affordable small radio telescope, and this radio telescope was made using a satellite dish, using a dish antenna dish. It was made using a low noise block down converter, which is called LNB, which is put right on that parabolic dish. Then we also used a set-top box receiver, which I did not explain here. But the set-top box receiver you can connect by one of the coaxial cable with the satellite finder that we have, and then you can use this radio signal that comes from sun, satellite, mobile tower, and light bulb with the help of this simplest of the radio telescopes. So I think this is one simple experiment which can help in popularization of astronomy, especially of radio astronomy among the young kids. I'm sure students at their age, they are very much fascinated about knowing the faraway objects. And I think this instrument, this will prove to be one of the very popular instrument if it is used regularly in physics. So I thank you very much, all of you. I thank you for your attention. And if there are some questions or something, I will be happy to answer.
Yeah, before we thank to the speaker, if participants have any question, they may ask. Or I request our judges, if any question.
Yes, Yogesh.
Yes, I think Professor Vijay sir may want to ask.
Sorry, I lost the voice.
Jaswant ji. Hello, can you
hear this one, sir?
Can you hear me?
Yeah, hello.
Jaswant ji, can you hear
Just a
me?
moment, sir. Yes.
Can you hear me? Jaswant ji.
No, I think there is an issue with the mic.
Can you remove your headphone, just one, sir?
Yes.
Yes, now is it audible?
Because
yes,
we are
please.
listening you very carefully.
Yeah, okay. Thank you very much. Yes.
Yeah, it was good presentation, very
Thank you.
innovative. And as a teacher, you should say this, okay, what you are teaching, which is affordable. But at the same time, you should make them cautious, okay. With the low cost, we cannot do the miracle, but certainly we can excite them. Okay.
Correct. So miracle. So I think, sir, means my point of this presentation was that miracle is relative.
Really.
Okay.
Correct.
So
yeah.
The exposure that one has, and then the new knowledge that we get, I think that can be miraculous for one. So
yes.
And means that is how you develop the interest.
Okay.
So
okay.
yeah, right. I agree that
my simple submission will be, when you talk about the sun, okay, using the dish antenna.
Yes.
Can you put a LDR along with the LND? Can you put a LDR or a simple photo detector, okay, to locate the sun using the dish antenna?
Right. So
you got my point. You got my point.
I got your point.
Yeah.
Yes.
So optical, and then
correct.
Then remove that LDR and go to the radio
correct.
using LND.
Yes.
Okay. So you are sure of getting radiation from sun.
Yes. Exactly. Yes.
Okay.
Right.
So improvise that, because you don't know where is sun, whatever the background, radio background is coming. Okay.
Correct. Yes.
But you are sure of the optical radiation.
Correct. Yes.
Okay.
So okay. So let me also.
In order to do that,
yes. Please.
You have to place couple of small mirrors on your dish antenna. to concentrate the optical light on LND.
Yes.
Okay.
Yes.
For radio waves, the whole dish is acting.
Correct.
Okay. So they will generate the confidence, because I'm not sure when there are many satellites are there.
Yes.
Okay. With GPS information, when you locate them, your dish on that particular angle, you are observing only the intensity which is coming on your reader.
Correct. I get that. Yes. Okay. So we are not going for accuracy in this. Okay.
Yes.
So what we are trying to do, this is like a popularization, science popularization kit.
Yes.
Okay. And since it was not available in radio frequency, since we have optical telescopes. Okay. So with optical telescopes, people have been observing, and I think they are quite popular at different places. So this is a small effort from,
So what I appreciate from your contribution, it's a wonderful, just add on the optical so that the confidence level increases.
Exactly. Yes.
Okay?
Thank you very much for your suggestion.
Whatever you are observing, that becomes meaningful,
Exactly. Yes. Right.
Okay.
So some of the
and then you can extend it. Then you can extend.
Yes. Right. So, yes.
So good. I appreciate your contribution.
Thank you very much. Yeah. Thank you very much.
Positive.
My pleasure.
So let us thank our speaker.
Thank you very much,
Jaswant sir, for giving your time to us. And
thank you very much. It's my pleasure always.
Yeah, wonderful presentation.
Thank you very much, ma'am. It's my pleasure. Thank you very much.
Okay. So now our next talk is based on study the variation of refractive index of laser light in different solution. And yes, it's me. So I request any of organizers if they can introduce us. If it's nobody, then
we welcome you.
Thank you, sir. So now, Ritu, can you share the screen? May I request? Yeah. First page. Can you make it big? And go to the first page. Yeah. Go to the first page, beta. So now, myself, Yogesh Kumar, along with Poonam Jain and Ritu Yadav, has performed this experiment. And this experiment I have performed because we faced a lot of problem in our lab because whenever we used to ask question based on refractive index, like if we ask how refractive index vary with the wavelength or frequency, or how the refractive index affect the temperature or pressure, then student usually fail to answer these kind of questions. So I realized that there is a need, urgent need of this experiment by which student can observe, do the observations based on some refractive index by varying some temperature in different solution of liquid and by varying the concentration of the liquid. Then they can realize some concept, and some concepts can easily cleared based on the refractive index. So our aim of experiment here is that we study the variation of refractive index of laser light in light like we have used red light here. And second, we just observe the temperature dependence of refractive index for different solutions. Here is the objective of our experiment is that we just have to make the phenomena of refraction easily understandable to the student through this experiment. Second, to make the student visualize the temperature dependence on refractive index for different solution, or also we can vary different concentration of the solution. Third, to show the student how different solution with different refractive index affect the path of light. Then it also helps the student to correlate the theory which they studied with the experimental work for better understanding the concept of refractive index. Student will also appreciate the relationship between temperature of the medium and scattering of light in that medium. Last but not least, to inculcate the skill of experiment, that is to validate and verify the concept, principle, and hypothesis related to the physical phenomena. So this experiment is actually the urgent need by which student can perform this experiment not only on the school level but also on the college level. By which we can easily understand. Otherwise, it is difficult to understand the concept of refractive index. So this experiment, the material we have used is very economically cheap and easily available at the home, as we have used a glass stirrer or a cylindrical glass chamber, or two semicircular protectors we have used. One CD is required and one laser light source, which is very easily available at the shop. And one stirrer is also needed, and thermometer we can also use. Now we have put some image. As you can see, there is some cylindrical beaker here. One CD we can have, and two protector, thermometer, and some pen and pencil we can use. Please go to the next. This is simply the demonstration we have used, and we will also play the video, whatever we have done. Can you go to the content, Ritu? Yeah. So now the question came into our mind: why and how does temperature affect the refractive index? So refractive index value are usually determined at some particular temperature. As like if higher the temperature, means the liquid becomes lesser and lesser dense, lesser viscous, which cause the light to travel faster in the medium. This results in the small value of the refractive index due to the small ratio, right? And second question, then why the refractive index changes with respect to the different concentration of liquid? So in a physical or chemical view, in a homogeneous solution or in a series of homogeneous form of liquid and or solutions, the refractive index depends on the power of interaction between the molecules. So the molecules move faster when temperature increases. And in this condition, the power of interaction between the molecules becomes lesser. Therefore, this mu depends not only on the temperature, but also on the pressure, composition, and strictly speaking, also the wavelength of the light. So frequency in this case is remain unchanged, which is irrespective of the medium, right? So next we can say that what factor affect refractive index? Like if I'm talking about the speed of light in the medium, lower is the refractive index because higher the speed of light in that case. And second is important that the temperature of medium. So when the temperature of the medium increases, the speed of light in that medium is also increases, and the refractive index is decreases. One most important point to note here is that, please note that this point, mu doesn't change with temperature, because earlier I said that with respect to temperature, refractive index is changed for different solution of liquid. But on the other hand, I'm saying that this mu doesn't change with temperature. Right? So mu doesn't change with temperature if density is kept the same. While temperature changes, pressure, then there is change in the refractive index. Otherwise, the refractive index cannot be changed if you change the temperature. So it is very important factor in our experiment. So using this now, come to the next slide. Yeah. So in this case, the solute concentration, like if I say that the refractive index increases with the concentration. So in the case of solute concentration, however, more molecule added into a solution, then of course, bigger the molecules are, the more of a chance that the light has hitting the molecules. So this slow down the light as it goes through the absorption and re-emission. It causes an increasing in the index of refraction. So this is a case which we have discussed in this. Now I invite Ritu so that she can demonstrate and explain our data. But we have done to calculate the refractive index for different solution and by varying the concentration of the solution. Ritu, you may proceed, please.
For giving me such an opportunity to present in here. So before going to the data, we are going to talk about the innovative aspect of this experiment. So as we know that refractive index is one of the most important property of a medium. And for this, we have equipments, very sophisticated equipments like refractometer. But we know there are schools in rural areas or schools run by NGOs that cannot afford such sophisticated equipments due to lack of infrastructure or finances or the inavailability of these resources commercially. So now we are going to talk about what is refraction or refractive index. The change in the direction of wave when passing from one medium to another caused by its change in speed and diverges from its original path. This process is known as refraction. The experiment is based on Snell's law. What does it say? It states that the ratio of sine of angle of refraction and sine of angle of incidence is always a constant, and that constant is our refractive index. As sir has already told you about how the temperature how temperature affects the refractive index. So for that we have devised this simple device in which we have joined two protectors together on a firm support. Here we have taken a CD and we have pasted it with a transparent sellotape. It is the most important tool in this experiment. Now, description of the experiment. We have already talked about our theory, and in theory we have talked about the Snell's law. And here we are going to talk about this formula which we have used in our experiment to find the refractive index. This is the formula which we are going to use. Now, procedure. Okay, for procedure, I'm going to start a video which we have made. Is the video visible to everyone, sir?
Yes, you can.
So is the video visible?
Yes.
Yes, play it.
Yes, yes.
Okay.
Good morning. So here first it is our setup where we have kept all the things. Here we have our salt solution in this. We have first properly mixed it, and then we are going to pour it in that. We have our tables, our equipments, the device which we have made with the protectors, stirrer, a laser pen, and the thermometer.
To the august audience, today we are going of refractive index of laser light in different solutions. We are also going to see the temperature dependency of refractive index for different solutions, the material used and the setup. So here we have used a glass.
As sir has already gave us the brief introduction of the materials, we're going to skip to the main part.
Laboratory thermometer, stirrer, and joined the two protectors together and pasted it on a clear CD, which we are going to use to measure the angles of angle of incidence and angle of refraction. To measure it for
first we are going to see what is the temperature. First we are taking it at room temperature. That is 30. That day it was around 30 degrees Celsius.
It is 35 degrees Celsius currently. For the experiment, now we are going to dip in that the device which we have created from CD and light on a particular angle and notice its refraction and note the respective values in the given table. We are going to incident it at angle of.
So here what we have done, that we have incident light at a particular angle, and we can see that it diverges from its original path. So here like we have taken at 60 degrees Celsius. So from taking the reference from 90 degrees Celsius, our angle of incidence is at 30 degrees Celsius.
30 degrees. Now we can see that after refraction, we are getting an angle of refraction of 21 degree. Similarly, we are going to do it for different angles, like for 40 degree. For 40 degree, we are getting an angle of 30 degree, angle of refraction. And for 50, we are getting an angle of 34.5 degrees. Now we will see the temperature dependency.
So now to check the temperature dependency of a refractive index, we are going to heat the liquid
of this solution, that is the salt solution which we have taken. We will see the temperature dependency of refractive index for salt solution. For this purpose, we have heated up the solution and now we are going to measure the temperature. We can see the temperature Celsius. For this temperature, we are now going to find the refractive index.
Since now we have measured the temperature, we first boil this solution and to a degree to 60 degrees Celsius. Now we're going to repeat the same process as we have done for the room temperature for different angles. Then we will slowly cool down the solution to 50 degrees Celsius, then repeat the process of incident of light and finding out the angle of refraction, and then we are going to repeat it for 40 degrees Celsius.
Now at 50 degrees Celsius, we are going to find refractive index. So we are going to incident it at 40 degrees, and we can see that the angle of refraction it is making is 35 degrees. We are going to calculate the angle of refraction similarly for 60 degrees Celsius and 40 degrees Celsius for an angle of 40 degrees. We have noted down all the values at room temperature as well as at different temperature for the salt solution. And at room temperature, we have found the refractive index of salt solution using red color laser light to be 1.337. Similarly, we are going to perform the experiment for sugar glucose solution and plot the graph for.
Okay, so now since we have seen the video, now we are going to jump to the our data which we have collected from the experiment. So first talking about the salt solution, we can see as the for different angles we have got our refractive index, and the refractive index comes out to be 1.337, and if we compared it to water, the pure water or distilled water, which is 1.33, it is 0.004 more. Now, and its temperature dependency, as discussed before, as the temperature increases, the optical density decreases, due to which refractive index decreases. We can see the same trend in here as we are for 40 degrees Celsius, it's 1.66, for 50 degrees Celsius, it's 1.12, and for 60 degrees Celsius, it is 1.05. The similar data which we have plotted for 10% of glucose solution. In this also we have we got the mean refractive index using laser light V to 1.35, And the trend in temperature, here also we can see it follows the same trend of temperature. As the temperature increases, the refractive index keeps on decreasing. Now we have got the data for 60% glucose solution. That is, we have increases the concentration of glucose in the water solution, which is turned out to be 1.39. And for the temperature, we can see that a similar trend in this also, as that the temperature increases, as the refractive index decreases. Okay, before jumping on to the
Ritu, just I want to mention one point here, that in case of the solute concentration, however the molecule added into a solution, and the bigger the molecules are, more of a chance of light has hitting the molecules. So this slow down the light as it goes through the absorption and re-emission, causing an increase in the refractive index. So we can see the directly dependence for the angle of refraction when we change the concentration, and what it will impact on the refractive index, as you can see in the table.
Okay, now we are going to plot the graphs for the given data. So how we know that the graphs are correct or not? Because for salt solution, we have never found any refractive index as such all over the internet, which we have seen. But we know that mu is equal to sin I upon sin R, which gives us a linear graph. So we can see that our graph is almost linear. So we can infer that our readings are quite accurate. Now now talking about the graph, see this, the last line, it is for glucose solution, 60% of glucose solution. The above line is for 10% of glucose solution, and the topmost line is for salt solution. Now talking about the second graph, that is the change of refractive index with temperature. As we have discussed that the temperature, as temperature increases, optical density decreases, due to which refractive index also decreases. And we can see that trend in this graph also. The above line is for 60% glucose solution. The second line is for 10% glucose solution, and the last line is for salt solution. So before going to the result, let us discuss the error percentage. Okay. As I told you before, that for salt solution, we haven't got the data. That means maybe we are the first one to do it for at the temperature for salt solution. But we have got the data for 10% glucose solution and 60% glucose solutions for room temperature. And we can see that the error is 0.7% for 10% glucose solution and 2.7 for 60% glucose solution. Also, if we see, okay, let me take back to the data. Also, if we compare this data with the pure water or distilled water, we can see that there is an increase in refractive index, as which sir also discussed with us, that as the molecule increases, as impurity increases, and impurity, we can take any alien substance which we have added. So as the impurity increases, the refractive index increases. So for the result, now what we have got in the result, that the refractive index of red laser light increases with increase in density of the solution. That is, salt solution has the least refractive index. Then we have 10% of glucose solution and maximum refractive index for 60% glucose solution. So when the light travels from air to denser medium, the speed of light decreases as a result of optical density increases. Second, the refractive index of the solution decreases with increase in temperature. We have discussed the reason for this many times, that when light passes through an optical medium, when the temperature rises, the optical medium expands. As the medium expands, speed of light increases in the medium, and thus the refractive index of the medium decreases. But okay, so experiment and observation is a part, but until and unless we make an analysis or inference from that experiment, that is also equally important. So what we infer first, apart from the temperature thing and the refractive index, we also see that as the temperature of the solution increases, the scattering of red light is visibly reduced, because as the temperature increases, the molecules moves apart, and so light can travel with greater speed without scattering. And secondly, as the impurity increases in liquid, refractive index of the liquid also increases. As I mentioned, that the bigger molecule, so the greater hindrance light gets and its speed slows down. So cost effectiveness and usability of this experiment. The proposed method is shown in the activities very much cost efficient as compared to other conventional methods using refractometer. Such experiments students can perform at their homes also. Refractive index is also the most important optical property of the medium. It plays a vital role in the areas of material science with special reference of thin film technology, fiber optics, underwater optical communication. The refractive index can provide information as about the behavior of light and the optical properties of the medium. The usability of this experiment is mainly for academic purpose for secondary and senior secondary school students, and can be incorporated in their lesson plans to make teaching more interesting and engaging. So by this experiment, first thing we get that we don't need very sophisticated or very expensive equipment for the experiments. It's about the innovation and creativity which you have in your mind, which can by simple tools also you can get the same or better results. So that is all from my side. Thank you, everyone.
So any question from the participant? Yeah, I can see one question. From Verma has asked, water used at different temperature for finding refractive index is same, or every time changes the water for different temperature? Very good question. Vikram Verma ji, as I have already mentioned that higher the temperature means the liquid become less dense and lesser viscous, because light to travel faster in that medium. So vice versa is also true that lower the temperature means liquid become lesser and has a lesser higher the viscosity. So this results in a larger value of refractive index due to the larger ratio. Okay, and so it will change if we increase the temperature for the same liquid. And another question for measuring the angle manually, like the holding the double D's normally to the surface of water, or I think we have to fix the double D's for less error in the measurement. Yes, of course, this is a mistake which we have done, I can say. Yes, if we hold this on some stand, then this experiment can be performed in a better way. Any other question?
I would like to ask you questions.
Yes, sir, please.
You are changing the temperature and measuring the various values, the angles of I and angle R. But it takes time to measure the value of the I and value of the R, and during that time, the temperature will be falling. What did you do to keep the temperature constant? Did you do something to keep the temperature constant during the observation?
No, sir. Actually, you are very right that every time this temperature is changing and there is no steady state. For this, we have some oven where we have kept this, where we can keep this beaker and kept this temperature constant by using the thermometer. So, but yes, if you will not use the oven, then of course the temperature will fall down. So we need some apparatus so that this temperature will maintain.
So may I like
तो
to
sir,
add?
yes.
Yeah, Ritu, you want to say something?
Yes, as you said, yes, the temperature would decrease. So we have taken a plus and minus one of like, we have started at for 50 degrees, we have started at 51 and went up to 49. And plus we have done this experiment multiple times because we know that the temperature would fall down. So we have also, multiplied the number of attempts so that we can get to a better average value.
Yes, still
That means आपने 51 टेम्परेचर पर भी लिया, फिर 50 पर लिया, फिर 49 पर लिया, और आपने देखा कि वैल्यूज ऑलमोस्ट कांस्टेंट आ रही हैं. यही किया आपने मेरे ख्याल में. तो ठीक है, पर जो है ना, ओवन इज नॉट ए गुड सॉल्यूशन फॉर कीपिंग द टेम्परेचर कांस्टेंट. देयर आर अदर मेथड, थर्मोस्टेट मेथड इज देयर, ठीक है ना, विद द हेल्प ऑफ व्हिच यू कैन ऑलवेज कीप द टेम्परेचर कांस्टेंट. Another thing is कि कंसंट्रेशन जो आपने ली है सभी सॉल्यूशंस की, जब आपने कंपैरिजन किया है तो जो कंसंट्रेशन ली है सभी सॉल्यूशन की सेम ली है या अलग अलग कंसंट्रेशन?
Different, sir. We have taken different concentration, like 20%.
मान लीजिए आपने एक साल्ट लिया और एक दूसरा शुगर लिया. शुगर एक साल्ट लिया, एक शुगर लिया. साल्ट की कंसंट्रेशन और शुगर की कंसंट्रेशन सेम रखी या नहीं?
Yes, it is same.
It is same, but it is not mentioned.
Experiment we have performed, it is same.
अच्छा. The parameters for everything are exactly the same.
Yeah.
Okay. तो एक थोड़ा सा आपने ये जो आपका पेपर है बहुत बढ़िया है. I will congratulate you and Yadav, who has performed the experiment under your guidance, and I think this is worth publishing in some journal, but there are certain typo mistakes, ठीक है ना. तो जैसे पहले उसमें उसने कहा है कि it is ratio of the sign of refraction to the sign of incidence. और बाद में ऑफ कोर्स ठीक लिखा है, म्यू इज इक्वल टू साइन आई ओवर साइन आर लिखा है, पर पहले जब आपने ये टाइपो में लिखा है, उसमें जो पेपर में लिखा है, उस पेपर में ये लिखा गया है साइन ऑफ रिफ्रैक्शन and sign of incidence is called as the refractive index.
It's a typo mistake, I think.
It is typo mistake. At two places the typo mistake is there. तो जब मैं recommend ये कर रहा हूँ कि इसको प्रिंट में डालना होगा, तो थोड़ी सी इसमें चेंजेस करनी पड़ेंगी. और दूसरा ये है कि जब इसको आप डिफाइन करते हैं साइन आई ओवर साइन आर इज इक्वल टू रिफ्रैक्टिव इंडेक्स, तो ये रिफ्रैक्टिव इंडेक्स किसकी है? किसकी रिफ्रैक्टिव इंडेक्स है? क्या ये एब्सोल्यूट रिफ्रैक्टिव इंडेक्स की बात कर रहे हैं या हम रिलेटिव रिफ्रैक्टिव इंडेक्स की बात कर रहे हैं?
सर वैसे हम इसमें रिलेटिव मीडियन की बात कर रहे हैं, नॉट एब्सोल्यूट.
हाँ, बिकॉज अगर हम एयर के विद रेस्पेक्ट टू मेजर करते हैं फिर तो हमारा ठीक है ये, पर अगर हम ग्लास टू वाटर करते हैं या वाटर टू ग्लास करते हैं तो ये रिफ्रैक्टिव इंडेक्स जो होगा वो रिलेटिव हो जाएगा.
वी हैव टू रिप्रेजेंट म्यू आर.
यस, तो आई थिंक जो है ना ये थोड़ा सा तो बस मेरे ख्याल में तो आपका बहुत बढ़िया वीडियो था, बहुत एक्सपेरिमेंट बढ़िया था, ठीक है ना. और मेरे से ज्यादा इंटेलिजेंट जो हैं वो भाई के विजय जी हैं, ठीक है ना. वो आपसे कुछ क्वेश्चन पूछेंगे तो
Thanks for your input, sir. Yes, Vijay sir, if you have any question.
Well, apology कि हम ज्यादा criticize ना करें. Well, the work is worth, okay, doing
superb,
and
sir.
following.
Superb, sir. Yes.
Superb. Yeah. तो इसमें हम innovation को यदि पकड़ें, तो what is the innovation? Okay. So the simplicity of the experiment is the innovation.
Yes.
Okay. तो आप उसको encash कीजिए, not the number. ठीक है. 1.3 कोई और भी निकालता है या 1.1 कोई और भी निकालता है. Temperature dependence and concentration dependence, large number of people have done it, and lot of data are available, okay, to verify. So my humble submission is claim your innovative tool. So Ritu bhi jab bata rahi thi and karke dikha rahi thi, तो उसमें what I find, ये जो laser pointer है ना, it has to be fixed and rotated. It has to go to 0. जहां कांटेक्ट बिटवीन द एयर एंड वाटर है, ओके, एंड दैट शुड बी फिक्स्ड। तो उसके लिए आप स्क्रू लगाइए, एक स्केल फिक्स कीजिए एट द सेंटर ऑफ दीज 2D एंड उसको आप रोटेट कर सकते हो, ठीक है, और लेजर को उस पर फिक्स कर दीजिए स्केल पे। ऑलराइट, नाउ इट बिकम्स अ innovative tool which is not available anywhere, which you can claim this is what you innovated, and you can use it anywhere. समुद्र में ले जाना, समुद्र में भी डिप करो और फट से लेजर घुमाओ एंड ऑब्जर्व इट, ओके। ऑफ कोर्स अभी जो आपने एक्सपेरिमेंट किया इन योर डेसिकेटर किया, जो अवेलेबल था आपको, बट समबडी कैन गिव यू अ बॉक्स पैरेलल शीट वाला रेक्टेंगल बॉक्स लीजिए फॉर डूइंग द एक्सपेरिमेंट, ऑब्जर्वेशन विच विल बी मच क्लीनर, ठीक है ना, और उसकी विड्थ यदि कम हो तो अच्छा है, सो दैट इट बिकम्स अ डिवाइस फॉर यू। रेक्टेंगल बॉक्स आसानी से मिलते हैं, और नहीं तो आप एक्रेलिक शीट का बनवा लीजिए, कांच का बनवा लीजिए, ओके। तो पर फिश टैंक जैसा होता है ना, तो छोटा सा फिश टैंक बनवा लीजिए, तो आपका यू थिंक 1000 रुपए, 1000 की जगह 1500 रुपए कॉस्ट हो जाएगी, एंड इट विल बिकम अ इनोवेटिव एक्सपेरिमेंट्स फॉर एनी यूजर, फॉर एनी स्कूल, ओके। तो अपने इनोवेशन को शेयर करना विद द क्वालिटी, आई एग्री विद सहजवानी सर कि रिजल्ट में टेम्परेचर का वेरिएशन है एंड कंसंट्रेशन क्या ली है, सो दीज क्वेश्चन विल ऑलवेज बी देयर, okay, so there are people who do research and publish के साथ एक एक पॉइंट पे डेटा लेके टेम्परेचर डिपेंडेंस पूरा निकाल के दिया है, okay, with some standard technique, but that is not the contribution. The contribution is the innovation of a simple device which can be rigged up and can be used in different schools to communicate the concept of variation of refractive index with concentration, then the solution, sugar and salt, is there any difference, okay, interatomic distance, temperature dependence. So all those parameters is secondary, okay, but your device, how you rigged it up, simplified it, okay, and gives you reproducible measurements, all right. That should be the emphasis. This is what I feel, because many people have tried the prism structure to study the refractive index variation and using the prism formula. All right, hollow prisms are available commercially. We have also done hollow prism experiment given in NGP 2-3 times. Okay, to do the only the lateral distances, no need of measuring the angle. Okay, with good approximation you can quantify, okay. So the idea is you should emphasize on what is innovative, okay, and this is what I refer, that you have made a device using these 2Ds so that incident angle and refraction angle can be seen directly, okay. I feel
innovation मैं suggest कर सकता हूँ,
जी जी,
एक innovation मैं suggest करता हूँ कि servo motors can be used with this. Servo motors बहुत आसान होता है, rotation and measuring the angle, automatic measurement of the angle will be there. That will be इन्होंने जो use किया है, इन्होंने जो use किया है बहुत simple सा use किया है, बहुत बढ़िया है. I mean I appreciate it.
So, while she was showing, तो I was hesitant कि वो कहाँ इंसिडेंट कर रही है, ठीक है ना, जीरो है कि नहीं है, बिकॉज एंगल मेजरमेंट सारा उसके ऊपर डिपेंडेंट है।
हाँ, वो क्योंकि हाथ तो हिलता ही रहेगा ना, हाथ तो हिलता रहेगा। हाँ, so stand and the servo motors can be used with this.
हाँ, वो रोटेटिंग आर्म आसानी से बन जाएगी।
बिल्कुल बिल्कुल।
Okay.
So honestly
Thank
speaking,
you, and all
I
the
just
best.
want to use some very low cost material so that students just
perfect. हाँ, एक स्क्रू लगाओ, प्लास्टिक का 5 रुपए का स्केल लगाओ, DKP, ओके, एंड उसको रोटेट करो जीरो पे, ठीक है,
बहुत अच्छा है।
Thank you.
Congratulations, sir. Congratulations.
Congratulations.
Yeah, very nice presentation and very nice inputs from our judges. We are so lucky to have you such intellectual inputs. I'm very much obliged, sir.
The value should be added in innovation.
Actually, this is the whole purpose of this convention. When people they are giving their inputs, they should learn, they should improvise, and we should have a publication.
Come out with good
something, and we do learn
with others.
And when you people comment, then we learn more. So this is yeah.
Vijay ji to gem hai.
So, so next presentation.
I thank Poonam ma'am and Ritu Yadav for helping me out to demonstrate this experiment in a very low cost, by using low cost material, so that student can understand the concept of refractive index by varying the temperature for different concentration of solution. Okay, so now I invite our other speaker, Mrs. Prem Kumari Narang. She is a PGT Physics from MIT International School, Mayur Vihar, and she will talk about how to measure the speed of light using chocolate bar. So, ma'am, please, you can present.
Sir, am I audible?
Yes, ma'am.
Yes.
Okay. Let me share my screen. I suppose my screen is visible to everybody?
Yes.
Very good afternoon to esteemed members of IAPT, respected judges, and my very learned colleagues. Myself, Prem Kumari Narang from MIT International School, Mayur Vihar, working as PGT Physics over there. First of all, I would like to thank all the IAPT members and the organizers of annual convention for inviting me here and providing me this platform where I can learn a lot from the learned people and expand my horizon. Thank you so much. I would like to begin the presentation with a thought. Anyone who stops learning is old, whether at 20 or 80. Anyone who keeps learning stays young. The greatest thing in life is to keep our minds young. So, respected all, let us all keep ourselves forever young and keep learning and keep growing. So, my experiment for today is to measure the speed of light using a chocolate bar. Yes, dear friends, only a chocolate bar. And it is not a low-cost device, low-cost experiment. It is very low-cost experiment. Can you just guess how much cost will be there to perform this experiment? Only 10 rupees.
10 rupees.
Yes, you heard it correctly. Only 10 rupees,
10 rupees.
and we are done with the experiment. And here it goes.
Microwave घर पे होता है.
Yes, microwave we are having at our home and in schools also. So we can perform this experiment with our kids in school because we are having microwaves in our kitchen of the school or a pantry, or you can say the home science lab, etc. So we can very well perform over there, or we can give this experiment as homework also to our kids. So let's begin. The material required for this: a bar of chocolate, a small bar of chocolate only of 10 rupees. And next we are having microwave and a plate. Obviously the microwave safe plate, and one flat bottom dish, or we can have this bowl. Obviously microwave safe. Only these are the material required to perform this experiment to find the velocity of light using a bar of chocolate. So procedure says, first what I did, first I removed the microwave turntable and the ring with the wheels from the microwave. The ring is there inside the microwave, and over that ring we are having one plate, glass plate. First we have to remove that. Fine. And this is the removal, how I remove this glass plate and that ring behind this glass plate. And the second step is we place the chocolate bar on the ceramic plate. This is not the ceramic plate. This is just the microwave safe plate. You can have this melamine sheet, or you can have this ceramic plate as well, and put this into the microwave. Actually, this plate will be touching that those wheels over the microwave. So to remove the connection between the plate and those wheels, we have to put one plastic dish so that the plate is raised over that turntable motor. So this is the assembly. First, I will put this upside down. This is a plastic dish, or we can have one bowl. This is one bowl. I have put this bowl over that turnable motor, and over that I have put this plate over this, and put this assembly inside the microwave. So very simple it is. Even a small child of class 4 or 5 can easily perform this experiment. And over this, like this, I have placed this plate over this, and I have to remove this wrapper from this chocolate, and I have to put this chocolate bar onto this plate. So this is the assembly of the experiment. Next, we run the microwave for around 40 seconds, and then look to see if there are many melted spots on the chocolate bar. Here I would like to clarify one thing. Actually, this experiment I have to do several times to check what is the minimum time required to melt and to have the spots only. Because instead of 40 seconds, if I run the microwave for 1 minute or so, then whole of the chocolate will be melted. That we don't want. So first we have to decide what is the, not decide, we have to check by doing some permutation and combinations. That is the minimum time required to just have those melted spots. But because we don't want to have that complete melted chocolate, we want to have only the spots. I will show in the figure also.
You get bubbles, or you get
not
bubbles?
Full 800 watt or whatever
Depression.
the high wattage is there, you can have it on that mode only. So this was the experiment that I was doing, keeping that inverted bowl and the plate and inside that chocolate bar, and I operated the microwave for around 40 seconds. And how much time is required, that depends upon the frequency of the microwave. And how do we know the frequency? Actually, on each and every box of the microwave, the frequency is mentioned over there. For my case, the frequency was 6.2 gigahertz. It was mentioned on the box. So every microwave is having its own specific frequency. We can have that data from the box. So for that frequency, 6.2 gigahertz, I needed 40 seconds to get those spots, melted spots on the chocolate. Then I use a ruler, simple ruler, to measure the distance between the middle of two adjacent melted spots of chocolate. And there are not only the two melted spots, there are several spots. From there we can take the measurement. So what we can do to be more precise, we can have different distances, and we have to have that the mean of those distances. That will give us the most accurate reading that we always do for our experiments. So we have to take two adjacent pairs to measure the distance between the melted spots of the chocolate. And here you can see in the picture. This is the chocolate not completely melted, but as you can see, or shall I show you from here? These are the melted spots. Yes. Here. Yes. One spot is here, as you can see, another spot here, and another spot here. Likewise, I got 8 to 9 spots over the chocolate. We can have different distances, and then finally we have to find the mean of these distances. On an average, I got, as you can see from the ruler, I got approximately 2.4 centimeter between the two, the distance between the two melted spots. Can anyone just give me the weird guess? What is this distance exactly in terms of wavelength? Any weird guess? Huh?
Lambda by 2.
Exactly. It is exactly lambda by 2. So this distance we can very well measure with the help of scale, and this is nothing but the half of wavelength for that particular microwave. Thank you very much, sir. And this is the half of the wavelength, the distance between two melted spots, two consecutive melted spots. As you can see over here, this is the complete chocolate bar, and here we got these spots. Here are the spots. One spot is this, one spot is this, and you can see more or less the distance between these spots is the same. More or less, I'm saying. More or less the distance between these spots is same. So for having most accurate reading, we can have just the mean of these distances. Fine. Now the observation part. We work out the speed of light using chocolate. We need to find the wavelength of the microwave inside. As the formula, the very basic one, we all know that C is equal to nu lambda. Nu is frequency, lambda is wavelength, and C is the speed of light that we already know. And in my case, my microwave has a frequency of 6.2 gigahertz. Now we can do the calculations very well. As you can see, let me have the pointer. Just give me a moment. First, we multiply the distance between the two melted spots on the chocolate by 2 by 2, because we have already learned that the distance between these two melted spots is lambda, half the wavelength. So to get the wavelength, first we will multiply that by 2. That will give us the wavelength for that particular microwave. And frequency we already know for the particular microwave, and the multiplying all these factors, we will get the velocity of light, speed of light. As you can see from the figure, this is the distance shown by this pink arrow, like this. The distance shown by this pink arrow and this pink arrow. This is the these are the spots of the melted chocolate, and this is nothing but the half of wavelength. And our microwave is operating at 6.2 gigahertz, 6.2 into 10 to the power 9 gigahertz. So this answer will come out in centimeters, because the distance between the two spots I have measured in centimeters. So to have the answer in meter per second, we have to divide it by 100. So our answer will be in meter per second. So here goes the calculations. See, distance between two melted spots multiplied by 2, because lambda by 2 multiplied by 2 will give us wavelength. Then the frequency of our microwave 6.2 gigahertz, and divided by 100 to make it in meters per second, the final answer. And if we multiply these two factors, 2.4 into 2 into 6.2 into 10 to the power 9 and 100, all these factors, that is the distance between the two spots was 2.4, and the frequency that is 6.2 gigahertz, and divided by 100 will give you the velocity of light in meter per second. This is the formula, the simple one. And here I get the answer. It is 2.97 into 10 to the power 8, and which is very close to the exact value of velocity of light. So we can have the final result. The calculations give us the value 297,600,000 meter per second, and which is close to the actual value of the velocity of light, which is 299,792,458 meter per second. And we can have the percentage error as well. So it gives us 0.73%. So the percentage error shows that how close we are to the exact value. So the results obtained by us are very accurate. So this is the experiment that we did only by using chocolate, and we can show this experiment, and we ask our children to perform this experiment at their homes also. So this was the experiment. Thank you, friends. And one more thing, if we are having some craving for chocolates, particularly the people having diabetes, this experiment can be performed by cheese slice as well. This will give us the same result. Thank you so much.
What did you say? कौन सी चीज? कौन सा alternative बताया sir? Madam?
Cheese slice, pizza cheese slice, sir.
अच्छा, cheese slide.
Yes.
Sir, sir, sorry for interrupting you.
Pardon?
Sir, please on your phone. Your phone is switch off. Sejwani sir.
मेरा phone तो ठीक है.
Sir, वो off हो रखा है. Please एक बार check कर लीजिए. Yes, ma'am. Rekha ma'am, you want to say something? I'm sorry for interrupting you.
Yeah, I can share this experiment. One of my student has done with papad.
Okay.
Yes, and those spots are very nicely visible, and you get more observations also. And this is a nice demonstration. Yes, just a sharing.
And how about the frequency, Rekha ji? Because I checked at microwave, whatever we teach is 2.4 gigahertz.
Yes.
Okay.
Yes.
Microwave. But
so whatever
ma'am has used the 6 megahertz.
Only for doing this experiment, you have to go by their specification. Otherwise, we can take it as the theoretical value also. It is just a demonstrating student how to, estimate something.
Estimate
it
something.
may not be. Yeah, it is just an estimation. Even if you need to have, I mean, repeatability is there because microwave, of course, has,
yes. Well,
different kind of
device.
It is a well-structured. It is a well-structured machine. So. Yes.
रेखा जी, मैं fortunately पापड़ का भी शौकीन हूँ और चॉकलेट का भी. तो
do the experiment.
दोनों experiment.
Not on the velocity of light.
Not on the velocity of light. और तीसरा जो नेम लिया चीज का, उसका भी मैं शौकीन हूँ.
Sir, enjoy. Sir, enjoy.
हाँ, तो actually जब आपने वो प्लेट हटाई जो है, और ताकि रोटेशन ना हो सके, ठीक है, दिस इज व्हाट यू वांटेड. और क्योंकि माइक्रोवेव का मैक्सिमा और मिनिमा आते हैं, तो जहां पर मैक्सिमा आया है वहां पर आपका स्पॉट नजर आया था. और जहां मिनिमा आए वहां पर भी शायद वहां स्पॉट नहीं था. ठीक है, तो ये
नहीं, वही λ/2 किया नहीं ना.
λ/2 किया ना.
हाँ, λ/2 किया है. वो बहुत ही अच्छा है.
एवरेज पावर मिनिमम पे भी है.
हाँ, मेरे दिमाग में एक्चुअली पहले बात आई थी कि क्या और भी कोई चीजें यूज की जा सकती हैं फॉर मेजरमेंट ऑफ दिस, पर आपने पहले ही जवाब दे दिया कि चीज से भी हो सकता है. क्या साबुन से हो सकता है?
Sir, we can try that.
अच्छा, जैसे कोई भी चीज जो
बर्फी पे कीजिए. Sugar molecule also absorb microwave.
There should be as a homework to find out the things that this experiment can be performed by different things. We can give as assignment to our children.
In which case, the reading will be more accurate.
Very good. हाँ. तो जिसका टेम्परेचर, मेल्टिंग टेम्परेचर हायर हो, उसके लिए ज्यादा टाइम हो सकता है. मतलब स्टूडेंट्स कैन ऑलवेज फाइंड आउट दैट टाइम आल्सो. हाँ. तो दिस इज गुड.
Thank you so much.
Because my liking for the chocolate and papad and the cheese.
This experiment would be a feast for you, sir. Then.
And Vijay ji will be more able to suggest many more things.
Certainly, the experiment and the quantification from the kitchen.
Yeah.
Okay, that has come on. So it's wonderful.
There is a lot of physics in kitchen, sir.
Kitchen.
Yeah.
Do not forget that.
Very true, ma'am. Very true. We know. Nanoscience is there.
Okay. Correct.
Main thing is that for this experiment, the teacher need not to come out from the kitchen. Experiment can be performed kitchen itself.
Right.
Actually, temperature you can learn from kitchen. The high flame.
Very true, ma'am.
Yeah.
Both
So,
microwave
Shashwani sir, can
absorption.
you switch on
प्रोफेसर
your
एससी
phone?
वर्मा जी भी जो ना प्रोफेसर एससी वर्मा जी भी बहुत सारे एक्सपेरिमेंट बताते हैं, उनमें वो बताते हैं कि कैसे किचन की चीजों को आप यूज कर सकते हैं और दूसरी चीजों को यूज कर सकते हैं. आई अप्रिशिएट एवरीथिंग. यस. हाँ,
Yeah, thank you so much.
विजय जी कोई मॉडिफिकेशन बताइए.
हाँ, बढ़िया, अच्छा लगा. वही मैं चेक करके आया. मैं देख रहा था चॉकलेट है कि नहीं घर में. अब चॉकलेट नहीं खाते. अदरवाइज हम वेरीफाई करते.
सर पापड़ तो जरूर होगा.
पापड़ जरूर.
मैं सिंधी हूँ तो पापड़ तो हमारा मेन डिश है.
यस सर. सर आपके लिए तो इमीडिएटली हो जाएगा.
Yes, good. It is very
Shazwani
good.
sir, can you switch on your phone? Shazwani sir, I would like to talk to you.
मेरा तो फोन ऑन है.
Sir, switch off. Please.
एक बार ऑफ करके ऑन कर लीजिए सर दोबारा से.
नेटवर्क प्रॉब्लम. It could be a network problem.
So
WhatsApp call कर लीजिए. WhatsApp call कर लीजिए.
Meanwhile, result is preparing for RC IEP.
Yes.
Thank all the speakers.
Yes.
Yeah.
And,
Just wait for 2 minutes.
I request Aluwalia sir or Rekha Ghorpade ma'am to say a few words, or any other speaker if somebody want to share his or her view. So I welcome everyone.
Sir,
Rekha ma'am, yes.
I was there throughout since morning and I really enjoyed all the sessions. And the best part was this RC-IEP. I think I must congratulate the RC-01 for conducting this particular activity, RC-IEP, because for last many years, we are doing this NC-IEP at the central level. And I was a coordinator for last 3 years also. And I know how much I was struggling to get the entries. And we have been telling RCs to organize this at the regional level and send the entries. But unfortunately, we were not getting that response. And I think your RC has taken the initiative, carried out this particular activity. And I'm sure that this is going to enrich enhance the registration at NCIP also. So this year we will definitely have more. So thank you so much for that. This not only triggers the minds of students and teachers. I was really enjoying because all the presentations were using things which were easily available at home. And this is what we want in innovation. Does not mean sophistication. That is what is the idea. We do not want sophistication. We do not want computers. We do not want any other this thing. But just by doing it, I mean, all the activities, I think, which were shown by even Dr. Singhal and other participants, they were wonderful. And keep doing this activity. My best wishes to you all, and send these entries to NCIP coordinator. This time, Dr. Geeta from Bangalore is the coordinator, and invite them for the convention at Patna. Patna convention dates are 2nd, 3rd, and 4th. Generally, we have on 2nd, that is the day before we inaugurate the convention, we have this NCIP competition set up ready. So probably 2nd December, the participants will have to report with their apparatus, whatever they have, and they are provided TA as per the IAPT norms, all the participants. So I think you can get in touch with Geeta madam and get the other formalities done, send the invitations to these participants so that they can appear there. And everything, the 2 days I think were really fruitful. They were not at all boring. I think I should really congratulate each one of you here. Seema madam, Poonam madam, Yogesh sir, Singhal sir, and I appreciate Professor Sahajwani. His presence, I think, has really added a lot of energy to your program. This is what is needed. His blessings, his guidance, his mentorship. And thank you, Professor YK Vijay. I should not thank you because you are my own IAPT family member
Yes,
at central
part
level.
of the
We to
family.
work together and we really make things very simple for us. So thanks for giving me this opportunity to, attend. Being online, I could really attend that. So that is another added advantage to all of us. So thank you and wish you all the best for everything. Thank you.
Thank
Thank you,
you,
ma'am.
Ghorpade madam. Sedwani sir, please look at the chat box. Sedwani sir.
Chat box.
Yes, sir, please.
Sir, please, yes, please read the chat box. Meanwhile, okay, Vikram Verma sir want to say something. He raised the hand. Yes, Verma sir.
Good afternoon, all of you.
Good afternoon.
First of all, I congratulate to all the members and all the judges and all the my learners colleagues for the wonderful sessions, and it was really wonderful sessions, and we learned a lot about that. And the most important part which I want to share, that today is a Sunday and we are free from all the worries and we are free from all the works, and we definitely attend the session we are definitely attend the session with the so attentively, and learned a lot about the sessions. And from the particular session which in which the participants presents their innovative work, and next year I will definitely participate in the event as a participant also. And lots of ideas we have taken today in the session, from the session, and put it down also. So again, I want to congratulate all the RC-1 members and all the judges and all the jury members, participants, and the resource person from the different states, cities. And once again, thank you so much, and thank you so much for the sessions.
Shazwani sir, can you hear us?
Yeah. तो आपको रिजल्ट चाहिए?
Yes, sir. Thanks. We have got the result from YK Vijay, sir. Your result is awaited.
Oh, I didn't know that I have to give the result also.
आपसे शेयर किया है.
Meanwhile, we can request
Surjan Singh sir,
YK Vijay sir to say a few words.
Well, I attended this morning session from 11 and it was really interesting. Single साहब के छोटे-छोटे observations काफी बढ़िया लगे. I thought it was the participation of one of the teacher, but no, he is the expert and doing wonderful job developing the videos for Verma sir. And well, the participation which I am supposed to evaluate, all the three contributions were really good and thought-provoking. But when I see the innovation, because many things we ignore, like the microwave cooking we have been doing and using, but when you try to make it quantitative, you have to give a thought, how to make it quantitative and use it with all the data. So as far as innovation is concerned, I think measuring the refractive index, you have developed the tool, okay? So that's the innovation that can go to the larger masses, okay? Direct measurement are available with the available things. The second innovative idea, using the dish antenna and looking at the radio telescope, is also a wonderful theme, okay? And it can be made quantitative, demonstrative, all right? Not so expensive, but the two things should be combined in it. As I said, one should develop a confidence, like optical focusing is so easy using mirror and parabolic concentrator, we can develop that. So along with the radio, if they integrate, then it will become a very good project, innovative project, which I think should be encouraged. And of course, there are a lot more from the kitchen to learn the science, fundamental science, so that I keep innovation in the third category. So this is what I share with all of you. Of course, the oral contributions were really wonderful, up to the mark to share at the national front. सिंगल साहब का एक ऑब्जर्वेशन जो लाइकोपोडियम पाउडर का शो करते थे ऑन ए लिक्विड ट्रांसपोर्ट, दोनों तरह का आयन कंडक्ट करते हैं, that is one thing. But if you change the polarity or they flip the magnet,
they reverse the direction.
the clockwise and anti-clockwise rotation, probably you can come across, okay, and talk about that Lorentz force in a more effective way. And if you add like mercury, if somebody has, okay, then you can talk about the charge transport and mass transport, okay, the electron flow in metal and the mercury ion flow in metal. So they have a different speed. In magnetic field, you don't see the depression at the electrode, but with ion, you see the depression. So that sort of extension can be made, okay? Even in gallium, that is seen, right? Okay. So while doing experiment is a wonderful theme in all these innovation, and that is what we are learning from D.P. Khandelwal's centenary celebration, that we should enjoy learning physics by doing, okay? And Verma Sahib is also advocating exactly the same way, that everywhere science is spread out. You have to just change your style of observation, okay? In every action, you find the science, all right? So I like to congratulate Seema ma'am for wonderful program you are having, okay? And thank you for giving me opportunity to exchange my views. I will be available whenever you call, you know. Thank you so much.
Thank you so much. And sir,
congratulations to all contributors, you know.
मैंने आपको WhatsApp पर रिजल्ट भेज दिया है.
Okay, just a second.
Yeah.
So, ma'am, before vote of thanks, may I request Seema ma'am, President IAPT RC-1, to announce the result?
Sir, Shaswani sir, I have not got your result as yet.
Oh.
But it was
1 minute, one minute.
or you can call me and tell me. I think your network is not working.
No. It's my mistake actually.
Yeah.
So
just give us 2 minutes, we'll announce the results.
I have kept my mobile on the flight mode. Now it will reach you.
Okay. And
because I don't want anyone to disturb me when I am in the conference. Yes. I think it has reached you. You have got it now.
So both the judges, they have announced the same result, though I just asked them separately. First winner is Yogesh Kumar, Ritu Yadav and Poonam Jain, refractive index, very well presented. And second is microwave by Prem Kumari Naran. And third is prize goes to radio telescope. So congratulations to all the winners, and your entries, 3 of the entries will be sent to the national level. That's my responsibility. So that you can meet you in Patna.
They can
and you can
demonstrate.
represent your work. Yeah.
And about the cash prize, because
Yeah, sir, you announce. Please, you announce.
because that I'm asking you, how do we give the cash prize? Either we give checks, and how will we deliver, or we transfer in the bank account? So that's
So you being treasurer, you decide and you announce.
so we will inform you.
Yeah,
how we
you can
the
send check.
prize money.
You can send check, to their account. Okay.
So we will inform you. We send,
There will
the
be
account details.
certificate of appreciation and participation. There is a cash prize first for 3,000, second for 2,000, and third one is 1,000, and we send to the participants by check.
Yeah.
So thank you all the
congratulations, everyone, all winners for RC-IAP. Now I would like to invite our Vice President, Shri Sujan Singh sir, for the vote of thanks. Please.
Sir, you are muted.
You are mute.
You are muted, sir.
Yes.
Sujan sir.
Yes, thank you very much, and very good afternoon.
Network.
Okay, meanwhile, please fill the attendance come back form. Request all the participants. The link has already been shared in the chat box.
Surjan Singh sir is joining in a minute.
Okay, ma'am. So till then, I request all the participants to fill the registration feedback form and attendance link.
And I must thank you, my whole team, and Rekha ma'am, Shazwani sir, YK Vijay sir, Singer sir. Amazing workshop. It's just because of the collaborative effort that we have been able to achieve all these entries. So I always thankful to PK Aluwalia sir and our OP Sharma sir, Srivastava sir. And let's wait for formal vote of thanks from Sujan Singh sir. But thanks so much for making this a very successful program.
Yes, sir has joined now.
He is muted.
Yeah. A very good afternoon to all of you.
Audible, please.
Hello.
Yes, sir. Yes,
Hello.
sir. You are audible. Yes, sir,
Yes,
you are audible.
am I audible?
Yes,
Yes, sir. Yes, sir.
perfectly audible.
Okay, okay. Actually, a very good afternoon to all of you. And मैं तो पहले थोड़ा हिंदी में बता दूं कि 2 दिन का जो ये प्रोग्राम रहा है, it was really amazing, and all the speakers, चाहे वो presenters हो जिन्होंने चाहे RCIP में अपना present किया हो या फिर general presentation दी हो, that was wonderful. And I learned a lot of physics from here. So many experiments which I have learned from you renowned academicians. Okay, now I am starting. On behalf of IAPT RC-1 Delhi and Haryana, I, Surjan Singh, a Vice President, IAPT RC-1, have a vote of thanks, formally a vote of thanks to you people as well. Now I am starting from 24th, in fact. Actually, my vote of thanks on 24th was at 10:50, and after that there were a lot of programs. So Professor YK Vijay sir, Director Center for Innovation in Science Teaching, IS deemed to be University Jaipur, and he is a judge today, and his innovative experiments in hub, that was a wonderful, and thank you very much, sir, for that. that you have given. You have actually shared your ideas, your knowledge with we people, and we are very thankful to you. And next is our respected Professor P.K. Ahluwalia, President IAPT National, and who gave a talk on use of classroom as a research laboratory, physics education research. And he told us that how we can make a classroom as a research laboratory. So this was a eye-opener to most of us, and we certainly will follow your techniques in the classroom to teach while teaching physics. Thank you very much, sir. Now, paper presentation on 24th. I have seen the paper presentation by Monica Sindhuvani, PGT Physics, making innovative teaching methods a part of classroom. And she has shared various videos through which we can teach a physics in the class. And the videos were wonderful. And thank you very much for that. Learning by doing by Professor Puspa Vindal ma'am, Professor Kalindi College, and similarly, experiential learning and integration in physics, again by Puspa Vindal ma'am. And these the concept which you have given, which you have presented on this platform were wonderful and appreciable. So I thank you, ma'am, for that on behalf of IAPT RC-1. And joy of learning physics through experiential learning and virtual tools. Similarly, a tool for experiential research figures pattern for science lab. So on 24th, we have learned a lot. And now from the beginning of this day, on 25th, that is today, we have started with the talk of Professor C.K. Ghosh. Unfortunately, due to the technical glitch, we were not able to listen completely, but that was amazing. And a big thank you to that for that user. And similarly, Mahesh Sethi sir, Department of Physics, Wilson College, Mumbai, Maharashtra. Ideas given by him were wonderful, and how a student, how a teacher can use these ideas in the classroom to clear the concepts of the students by developing a knowledge of order of magnitude and scaling. That was good, that was wonderful and really amazing. And a big thank you for that user. Innovative experiment by our Dr. S.K. Singhal sir. As usual, I know him very well. He's a master of experiments, in fact, I can say. And he has used, he has shown the brilliant actually videos to teach physics through a small things. And wonderful. And thank you, Singhal sir, for sharing such wonderful videos with us. Now, this RCIEP presentation given by Prem Kumari Narang ma'am, PGT Physics, MT International, Mayur Bihar, and how we can teach the student to estimate the speed of light. Actually, I have seen first time this experiment in my life. After teaching physics approximately 25 years, and this was very low cost, you really and truly said this cost nearly 10 rupees. And it was a wonderful experiment which we can tell the student they can perform this experiment at their home as well, and they can gather the idea how to calculate, how to estimate the speed of light. And a big thank you for that, ma'am. And similarly, variation of refractive index of laser light in different solution. I know Poonam ma'am, Yogesh sir, Dr. Yogesh sir, Dr. Poonam ma'am, but wonderful contribution of their student, Ritu Yadav. And this was a really low cost experiment through which we can give the idea to the students how refractive index of laser light varies with temperature and in different solution. very low cost activity, and certainly I appreciate the efforts of the judges who made different innovation in that, who suggested that these innovation can be incorporated in that, and certainly the accuracy of the result will increase. So scope of improvement is always there, but wonderful experiment, wonderful efforts, nice efforts. Yogesh sir and Ritu Yadav, Poonam ma'am, very, very big thank you to you people, because you have shared your learnings, your findings on this platform, and we learned a lot from you people. And Jaswant sir, Jaswant Kumar Yadav sir, really you have done a very I can see that the contribution of Jaswant Kumar Yadav sir was a good optical actually telescope, and how to, we can say that, take the data, we can conclude, we can how we can use that telescope, how we can make a telescope, and what are the data. So really it's good. And last but not the least, our judges, Vijay sir, Yogesh Kumar Vijay sir, and Sahajwani sir, and the valuable contribution of our from our secretary and National IAPT Sri Ma'am Rekha ma'am. Your contributions are big and are always appreciable, and we do appreciate. We have a big thank you for you people, that you have made a tremendous success of this efforts, this convention of IAPT RC-1, and it will be unjustified on my part that if I'll not recall all those people who have done brilliant efforts in making this workshop a successful program. Being a member of IAPT RC-1, it is my duty to thank all RCs, national IAPT team, and all other members, all the members who have joined us throughout on 2 days for this program, and which was planned, which was executed by our team by working hard day and night. I appreciate, I thank our president, Mrs. Dr. Seema Vats, who have done brilliant efforts to make this program a great success. And under her guidance, we worked a lot. Our technical team put their day and night efforts to make this program successful. But without the support of the audience, every program is incomplete. Here, audience what is not suitable, because the audience means the person who have attended this program. The person means the physicist, the physics students who have attended this program, and they have given their valuable contributions for the innovation and for this improvement of the ideas which were shown by the presenters, paper presenters, or their experiment or innovation ideas presented by them. A big thank you to all. And similarly, I always actually have this in my mind, that everyone who was a part of this program really deserve a big thank you from our side. So thank you very much. Thank you very much. Thank you all, and have a good day, great day ahead. Now it's over to Yogesh sir.
Sir, can I say something? Please allow me to say.
Yeah.
I want to say that the original idea was of Poonam ma'am. I just performed the experiment, so I would like to thank Poonam ma'am and Yogesh sir for giving me this opportunity and considering me as liable to that I can perform and present this. Thank you so much, ma'am and sir.
Okay.
It's all from my side now. Now Yogesh sir, you can continue.
Yes.
But actually मैं फिर भी मैं ये कह देता हूँ, मैं फिर भी बहुत अगर मेरी तरफ से सॉरी है अगर मैं किसी का नाम नहीं ले पाया, क्योंकि बड़ी लंबी लिस्ट है, और ये जो प्रोग्राम 2 दिन का था, बहुत लोग इसमें हमारे साथ जुड़े, बहुत टीचर्स ने बहुत कंट्रीब्यूट किया, और जिन्होंने पेपर प्रेजेंट किया उन्होंने तो किया ही है। Yes, sir.
Sir, your presence is self-explanatory. मतलब we need not mention.
Yes, sir. Yes, sir.
योगेश सर, आप एक नाम भूल गए, सुरजन सिंह ने अपना नाम तो लिया ही नहीं।
हाँ, वही सर मैं कहना चाह रहा था एक्चुअली।
तो सर का नाम रह गया।
क्या है?
मनोज कौशिक सर का रह गया।
हाँ, नाम तो
मनोज कौशिक सर।
मैंने क्या किया, नाम इसलिए लिए ही नहीं क्योंकि नाम बहुत लंबे, मैंने एक
सुरजन सिंह जी आपका नाम तो रह गया। आपका थैंकफुल भाई, ऑल ऑफ अस आर वेरी थैंकफुल टू यू कि आप यहाँ आ जाए, क्योंकि सर का भी शेड्यूल बहुत बिजी रहता है, मुझे पता है। एज ए प्रिंसिपल whenever I met with him, हमारा उनसे साल में 1-2 बार तो जाना हो जाता है वहाँ पर के स्कूल में। तो he was so much busy even that we were in the school, तब भी सर बहुत कम, क्योंकि कंटिन्यूअसली शेड्यूल सर का ऐसा रहता है। तो सर ने टाइम निकाला।
मतलब आप ये कहना चाहते हैं यहाँ पर सबके सामने कि हम इनके स्कूल में जाते हैं, हमें पूछते हैं, मतलब कुछ भी
Sir, please, let's end the meeting here. And special thanks to Manoj Kaushik sir and Vandana Banga, OP Sharma sir,
Yes,
sir, Vikas Mittal sir, and whole team of EC.
Yes,
that is
whole team.
Ma'am Javi sir. So this completes the whole team now, and end the meeting.
Okay, so before signing off formally, first of all, I would like to congratulate all the winner of RC-IEP and all the best to the participant, and thank you all the speakers, paper presenter and participants of RC-IEPs for enlightening the audience with their knowledge. Also, this event is not complete without mentioning a big thanks to our audience for making this annual convention a great success. Thank you, everyone.
Thank you, and wish to hope to see you again.
रेखा मैम, थैंक यू वेरी मच।
Thank you.
आप आए, बड़ा अच्छा लगा, और आपने ज्वाइन किया।
It was my pleasure. It was my pleasure because I got lot of 2 fruitful days to listen to you, and it was a really good experience for me. Because first time I think I have attended the convention by RC-1, and it's a good practice. I think it is worth emulating by other RCs, which we are going to definitely see.
I think there were more than 65-70 participants.
Yes,
each one has contributed.
It was a great success in terms of participation.
Yes. On YouTube also there were more than 120.
Or Sehajwani
so
sir,
if you add the two, then number is quite good.
That's really great.
Very good.
Thank you.
Okay, thank you everyone.
Hope to see you again soon physically.
Yes.
Yes sir, yes sir.
मैंने आपसे बहुत कुछ सीखा।
पटना में तो मिलेंगे. Hope to see you all in Patna.